What if the most important thing about an ancient ruin is not what it reveals, but what it refuses to reveal? For centuries, archaeologists have uncovered cities, temples, fortresses, tombs, and monuments from every corner of the world. Each discovery answers a question, but almost every answer creates several new ones. A structure survives, yet its purpose remains debated. A civilization leaves behind extraordinary architecture, yet almost no record of how it was achieved. A site is excavated for decades, only for new evidence to completely change its story. The ancient world has a way of turning certainty into mystery, because beneath every layer of earth lies another layer of questions. And despite everything we have discovered, some of the most fascinating parts of humanity's past may still be waiting to be understood. Northwestern Tunisia. A mountain of golden marble supplied some of the greatest monuments of the Roman Empire. More than 2,000 years later, archaeologists still debate how ancient engineers extracted, shaped, polished and transported stone on an industrial scale without modern machinery. Ancient Chemtu, known in antiquity as Simithus, was identified through archaeological investigations beginning in the 19th century. Excavations later revealed vast quarry complexes, workshops, roads, hydraulic systems, and evidence of one of the largest marble industries in the Roman world. Chemtu was unlike most ancient cities because its importance came from the mountain itself. The site contained deposits of Numidian marble, known to the Romans as *giallo antico*. Characterized by striking yellow, gold, and reddish veining, it became one of the most valuable decorative stones in the empire. Ancient authors described it as a luxury material reserved for imperial projects, temples, and elite architecture. What makes this remarkable is its distribution. Marble from Chemtu has been identified hundreds and sometimes thousands of kilometers from its source. It appeared in Rome, Ostia, and numerous provincial cities throughout the Mediterranean. Today, transporting a single 50-ton stone block requires heavy trucks, cranes, specialized permits, and carefully planned logistics. Yet Roman engineers moved enormous quantities of marble across an empire spanning more than 5 million square kilometers. The first mystery is simple. How did a quarry located deep inside North Africa become one of the primary suppliers of decorative stone for an empire stretching across 3 continents? At first glance, quarrying appears straightforward. Remove stone from a mountain and transport it elsewhere. In reality, the process is far more complicated. Modern quarry operations rely on diamond wire saws, hydraulic splitters, explosives, and computerized cutting systems. Yet Roman quarry workers possessed none of these technologies. Even so, evidence from Chemtu demonstrates that workers extracted blocks weighing tens of tons with surprising precision. Archaeologists have documented quarry faces containing long, straight extraction channels. These grooves reveal careful planning and highly controlled cutting methods. Workers likely used iron tools, wedges, hammering techniques, and systematic fracture control. The challenge is understanding how they avoided catastrophic failures. Stone is unpredictable, and hidden fractures can destroy months of work instantly. Modern engineers use geological surveys and advanced imaging technologies to identify weaknesses before cutting begins, while ancient quarry workers relied entirely on observation and experience. Even today, experimental archaeologists attempting to reproduce ancient quarrying techniques often discover that apparently simple methods require extraordinary skill. Small mistakes can split a block incorrectly, reducing its value dramatically. Chemtu suggests generations of accumulated practical knowledge that was rarely written down and has largely disappeared. Perhaps the most astonishing achievement was not quarrying but transportation. Some marble blocks likely weighed between 20 and 60 tons, while larger examples may have exceeded 100 tons. To understand the scale, consider that an African elephant weighs roughly 6 tons. A 60-ton marble block therefore weighed approximately as much as 10 adult elephants combined. The blocks first had to be moved from the quarry itself. They then travelled toward river systems, reached ports, crossed portions of the Mediterranean Sea, and finally arrived at construction sites. Roman engineers achieved this without diesel engines, hydraulic cranes, steel cables, or modern roads. Researchers estimate that moving large stone blocks often required hundreds of workers, specialized sledges, rollers, lifting devices, and carefully organized labor systems. The mystery is not whether the Romans transported these stones, because the marble survives as proof. The mystery is how they accomplished the process so efficiently and repeatedly for centuries. Before extraction could begin, quarry managers needed to understand the mountain. Not every section of marble possessed the same quality. Decorative stone was valuable because of its color consistency, structural integrity, and visual appearance. Modern geologists use seismic imaging, ground-penetrating radar, and three-dimensional modeling to locate promising deposits. Ancient quarry workers possessed none of these technologies, yet they repeatedly targeted areas containing some of the most visually attractive marble available. How they identified the best sections remains uncertain. Some researchers believe Roman quarry specialists developed sophisticated observational techniques based on surface patterns, fracture behavior, coloration, and geological experience accumulated across generations. If true, much of this knowledge disappeared with the collapse of the Roman industrial system. Of all Chem2's technological puzzles, none may be more fascinating than what happened after extraction. Cutting stone was only the beginning. The true challenge was transforming rough marble into polished architectural masterpieces capable of decorating imperial buildings. Visitors to Roman monuments often focus on columns, statues, and architectural grandeur, yet the surfaces themselves represent a technological achievement that remains surprisingly difficult to explain in detail. Many surviving examples of Numidian marble exhibit extraordinarily smooth finishes. Even after nearly 2,000 years, some surfaces continue reflecting light with remarkable effectiveness. Creating such finishes requires removing microscopic imperfections from the stone. Modern stone processing facilities accomplish this through electrically powered polishing systems using carefully engineered abrasives. Computer-controlled machinery applies consistent pressure while rotating polishing heads gradually refine the surface. Ancient craftsmen possessed none of these tools, yet they achieved results that still impress modern conservators. Researchers believe workers employed a sequence of increasingly fine abrasives. Quartz sand, emery, crushed minerals, and specialized polishing compounds have all been proposed. The problem is that no complete ancient technical manual survives explaining the exact process. Experimental archaeology has produced intriguing results. Teams attempting to recreate Roman polishing techniques discovered that achieving mirror-like finishes can require enormous amounts of labor. Hours become days, and days become weeks. The process demands not only materials but also highly developed expertise. Pressure must be carefully controlled, the abrasive sequence must be correct, and surface irregularities must be identified and removed. Even slight mistakes can ruin the final appearance. This raises a fascinating possibility. Perhaps the most valuable resource at Chem2 was not marble itself, but skilled human knowledge. A master stone finisher may have possessed techniques acquired through decades of apprenticeship. Such knowledge could have been transmitted directly from craftsman to craftsman without ever being formally documented. If that transmission chain breaks, the knowledge disappears. This pattern appears repeatedly throughout history. The formula for Roman marine concrete remained poorly understood for centuries. The manufacturing techniques behind Damascus steel continue generating debate. The mechanisms used to construct certain megalithic monuments remain controversial. Chem2 may belong to the same category. The marble survives, but the craftsmen do not, and with them may have vanished some of the most sophisticated practical knowledge of the ancient world. Chem2 was far more than a local quarry. Large extraction areas, workshops, transport networks, and worker settlements reveal a vast, organized industry. Managing labor, supplies, transportation, and quality control without modern technology required remarkable coordination. That this system operated successfully for centuries remains one of the great achievements of the ancient world. What do you think? Were the achievements of Chem2 simply the result of generations of accumulated experience? Or did its craftsmen possess specialized technological knowledge that has largely been lost to history? Let us know your thoughts in the comments below. Tunisia's Kapon Peninsula, overlooking the Mediterranean Sea, is home to Kerkuena, an ancient Punic city abandoned more than 2,200 years ago. Unlike Carthage itself, it was never rebuilt by the Romans. What survived is a rare snapshot of a civilization whose technological knowledge may have been far more advanced than history remembers. Although local ruins had been known for centuries, systematic excavations began in the 1950s. Archaeologists soon realized they were uncovering something extraordinary, one of the best preserved Punic cities ever discovered. Destroyed during the First Punic War, around 250 BC and never reoccupied, Kerkuena preserved streets, houses, workshops, drainage systems, and industrial facilities almost exactly as they existed in antiquity. What researchers found raised an unsettling question. How sophisticated was Carthaginian technology before it vanished? The first puzzle appears from above. Many ancient cities evolve gradually, with streets twisting around older structures and neighborhoods expanding without central planning. Kerkuena appears different. Archaeological surveys reveal organized districts, standardized residential layouts, and carefully aligned streets. The urban design suggests deliberate planning rather than random growth. This is remarkable because no Punic engineering manuals survive, no city plans exist, and no construction records have been discovered. Yet the city demonstrates an understanding of surveying comparable to Greek colonial settlements of the same era. Modern surveyors use satellites capable of measuring positions within centimeters, while Punic planners relied on geometry, observation, ropes, poles, and practical experience. Nevertheless, they created an organized urban landscape that remained functional for centuries. How they achieved such precision remains largely unknown. Water was perhaps the most valuable resource available to Kerkuena. The Kapon Peninsula experiences hot summers and periodic droughts, making careful resource management essential for maintaining a permanent urban population. Excavations revealed numerous cisterns, drainage channels, bathing facilities, and water storage systems integrated into private homes. These discoveries suggest that water collection and distribution were not improvised solutions, but fundamental elements of urban design. Researchers believe rainwater harvesting may have played a major role. If true, Kerkuena represents one of the earliest examples of large-scale urban water conservation in the Western Mediterranean. The mystery lies in efficiency. Without pumps, filtration systems, or modern engineering calculations, the inhabitants created infrastructure capable of supporting an entire city. Many details of how the system operated remain uncertain because the organic components that may have connected various sections disappeared long ago. One of Kerkuena's least discussed technological achievements involves temperature control. Many houses contain central courtyards surrounded by living spaces. At first glance, the design appears aesthetic, but in reality it functions as an effective climate control system. Modern architectural studies show that courtyard houses can reduce indoor temperatures by several degrees Celsius through shade, airflow circulation, and thermal mass effects. The thick walls discovered at Kirkwayne likely absorbed heat during the day and released it gradually after sunset, creating a naturally regulated indoor environment. Today, sustainable architects often promote passive cooling as an innovative solution to climate challenges. The people of Kirkwayne were already using similar principles more than 22 centuries ago. The question is whether these solutions emerged through generations of experimentation or through theoretical knowledge that has since disappeared. Among all of Kirkwayne's technological puzzles, none may be more fascinating than the production of Tyrian purple. Archaeologists have uncovered enormous accumulations of crushed marine shells, industrial processing areas, and evidence of large-scale coastal manufacturing. These discoveries suggest that Kirkwayne may have participated in one of the most valuable industries of the ancient world. Tyrian purple was not simply a colour, it was a technological achievement. Ancient sources describe the dye as more valuable than gold by weight in certain periods. Roman emperors restricted its use because it symbolized power, wealth, and authority. The mystery begins with the raw material. The dye came primarily from sea snails belonging to the Murex family, and each snail contained only a tiny gland producing the precursor compounds required for the dye. Experimental studies suggest that thousands of snails were needed to produce even a few grams of pigment. Some estimates indicate that approximately 10,000 to 12,000 mollusks might be required to generate enough dye for a single ceremonial garment. The process itself was astonishingly complex. Workers had to extract microscopic glands from each shell, after which the material was subjected to controlled decomposition. Temperature had to remain within a relatively narrow range. Exposure to sunlight triggered chemical transformations, and oxygen levels influenced the final coloration. Small variations could produce shades ranging from blue to crimson to deep purple. Modern chemists now know that the primary colouring compound is dibromoindigo. What remains astonishing is that ancient producers mastered this process without chemistry laboratories, thermometers, microscopes, or analytical instruments. Researchers can identify the chemical reactions today, but they cannot fully explain how ancient craftsmen discovered and standardized the process in the first place. The challenge becomes even greater when considering scale. The shell deposits found across Punic sites contain millions of fragments, indicating industrial production. Industrial production requires consistency. Consistency requires quality control, and quality control requires technical knowledge. Yet, almost no written technical documentation survives. The comparison often made is with the Antikythera mechanism. Both technologies appear unexpectedly sophisticated. Both demonstrate knowledge far beyond what many people assume ancient societies possessed. And both raise the same question: how much practical scientific knowledge existed in the ancient Mediterranean that later vanished? The purple dye industry reveals another mystery: logistics. Producing large quantities of dye required organized labor forces, transportation networks, fishing operations, storage facilities, and trade connections extending across the Mediterranean. The city functioned as part of a commercial system linking North Africa, Sicily, Sardinia, Spain, and the Near East. Maintaining such a network without modern communication systems would have been extraordinarily difficult. Yet Carthaginian merchants successfully coordinated trade across thousands of kilometers. The mechanisms behind this coordination remain only partially understood. Another puzzle involves construction materials. Many surviving structures endured centuries of exposure to salt-laden winds, humidity, and seasonal weather changes. Marine environments are among the most destructive conditions for architecture, yet portions of Kerguelen remain remarkably preserved. Researchers continue studying the mortars, plasters, and coatings used by Punic builders. Some materials display durability that exceeds expectations. Like Roman concrete, they suggest a level of practical material science that is still not fully reconstructed. The exact recipes remain uncertain, and the craftsmen who created them left no instructions. Do you think the secret of Tyrian purple was simply the result of centuries of trial and error? Or did the Carthaginians possess scientific knowledge that was lost when their civilization disappeared? Share your thoughts in the comments below. Central Nigeria. Thousands of years ago, deep inside a landscape of caves and rocky hills, a civilization appeared that could smelt iron, create life-size sculptures, and organize large-scale production long before many neighboring societies entered the Iron Age. Yet they left no written language, no engineering manuals, and no explanation, only mysteries. Today, the Nok Cave complex remains one of the most intriguing archaeological puzzles in Africa, raising a question that still challenges researchers. How advanced was the lost technology of the Nok people? The Nok civilization was first identified in 1928 when miners searching for tin in central Nigeria unexpectedly uncovered unusual terracotta sculptures buried beneath the soil. Subsequent excavations revealed a much larger culture dating between approximately 1500 BC and 500 AD. Archaeologists later discovered caves, habitation sites, furnaces, iron artifacts, pottery workshops, and hundreds of terracotta fragments scattered across a vast region exceeding 70,000 square kilometers. What emerged was evidence of one of the earliest complex societies in sub-Saharan Africa, but the discoveries created more questions than answers. Among all Nok achievements, none are more astonishing than the terracotta figures. Many stand nearly 1 meter tall, and some depict human beings with elaborate hairstyles, jewelry, facial expressions, and geometric designs so precise that they appear almost modern. The sculptures are typically hollow, suggesting their creators understood structural stresses during firing. This may sound ordinary today, but it was not. Large clay sculptures are extremely difficult to manufacture. As moisture escapes during drying and firing, internal stresses develop. If the walls are too thick, the sculpture can explode. If they are too thin, it can collapse. Uneven heating creates fractures, while poor clay composition leads to deformation. Modern ceramic artists use controlled kilns, thermometers, and carefully refined materials to reduce these risks. The Nok people possessed none of these technologies, yet many sculptures survived. This raises one of the greatest technological mysteries of ancient Africa. How did they achieve such consistency? Researchers believe Nok artisans intentionally selected specific clay deposits with favorable mineral compositions. Some analyses suggest the clay was carefully prepared before shaping, indicating an understanding of material properties developed through generations of experimentation. Even more impressive is the artistic standardization. Across hundreds of kilometers, sculptures display similar stylistic characteristics. Eyes are often represented by triangular or circular openings. Facial proportions follow recurring patterns, and decorative motifs appear repeatedly. Such consistency suggests either extensive communication between communities or specialized craftsmen transmitting knowledge across generations. The comparison with other ancient civilizations is striking. The famous terracotta warriors of China date to the 3rd century BC, yet many Nok sculptures may be centuries older. Unlike the Chinese figures, however, The Nok statues were produced without imperial workshops, written instructions, or centralized bureaucracies that we know of. The knowledge system responsible for their production remains almost completely invisible, and that is perhaps the greatest mystery. The sculptures survived, but the technology behind them did not. The Nok culture is frequently associated with some of the earliest evidence of iron production in sub-Saharan Africa. This discovery transformed archaeological understanding of African technological history. Producing iron is not a simple task. Iron ore must be heated to temperatures approaching 1,200 degrees Celsius, and achieving such temperatures requires sophisticated control of furnace design, airflow, fuel quality, and ore selection. Even modern experimental archaeologists struggle to reproduce ancient iron-working techniques without extensive preparation. Excavations have uncovered furnace remains, slag deposits, and iron artifacts indicating sustained metallurgical activity. The volume of slag found at certain sites suggests production occurred on a scale far beyond occasional toolmaking. Yet no written records explain how Nok metalworkers mastered this process. One of the biggest debates concerns the origin of the technology itself. Did Nok communities independently develop iron smelting, or was the knowledge introduced through long-distance cultural exchange? Decades of research have failed to provide a definitive answer. If independent invention occurred, the Nok people achieved one of humanity's most important technological breakthroughs entirely on their own. Technology rarely exists in isolation. Iron production requires miners, terracotta production requires clay specialists, large communities require food producers, and trade requires organization. The Nok archaeological landscape reveals evidence of all these activities. What remains unclear is how such knowledge was transmitted. Without writing, technical information had to pass orally. Generations of craftsmen may have spent decades mastering techniques before teaching apprentices. Entire technological systems could therefore disappear if social structures collapsed. This possibility may explain why so much Nok expertise seems lost today. We can see the products, but we cannot see the instructions. The caves themselves present another puzzle. Archaeologists have discovered evidence suggesting that some caves were occupied, while others may have served ceremonial functions. Certain locations contain pottery fragments, charcoal deposits, and artifacts indicating repeated human activity. Yet many caves occupy difficult positions that offer little practical advantage for daily living. This has led researchers to propose alternative explanations. Perhaps the caves served as ritual centers. Perhaps they functioned as refuges during conflict. Perhaps they stored valuable resources. Or perhaps they played multiple roles over centuries. The available evidence remains incomplete, and as a result, the true purpose of many Nok cave sites is still debated. One often overlooked mystery concerns organization. The Nok cultural area covered tens of thousands of square kilometers. Maintaining artistic traditions across such distances would have required communication networks, movement of people, and shared cultural standards. Today, similar coordination depends on roads, telecommunications, and written administration. The Nok people possess none of these systems as far as current evidence shows, yet their cultural identity remained remarkably consistent. How information moved across this landscape remains largely unknown. Around the middle of the first millennium AD, the Nok culture gradually vanished from the archaeological record. No evidence points to a single catastrophic event. No massive battlefield has been discovered, and no definitive proof of epidemic collapse exists. Climate change, environmental pressures, migration, and social transformation have all been proposed, but none fully explain the disappearance. The result was the loss of one of Africa's earliest technological traditions. Knowledge accumulated over centuries simply faded from history. What do you think? Were the Nok people simply master craftsmen, or did they possess technological knowledge that was centuries ahead of their time? Share your thoughts in the comments below. Cyrene, on the Green Mountain Plateau of northeastern Libya, should never have become one of the richest cities in the ancient Mediterranean. Built hundreds of kilometers from major rivers and surrounded by semi-arid landscapes, the city somehow sustained tens of thousands of people, constructed monumental temples rivaling those of Greece itself, and controlled a biological resource so valuable that ancient writers compared it to silver. More than 2,000 years later, archaeologists can still walk through its streets, study its engineering, and measure its monuments. Yet some of the most important questions remain unanswered. How did Cyrene master water management in such a difficult environment? How did its builders move enormous stone blocks across rugged terrain? And perhaps, most mysterious of all, what exactly was silphium, the legendary plant that made Cyrene one of the wealthiest cities in the ancient world before disappearing forever? Founded around 631 BCE by Greek settlers from Thera, Cyrene grew into the leading city of the region known as Cyrenaica. Systematic archaeological investigations began during the 19th century and expanded significantly throughout the 20th century under Italian, British, American and Libyan teams. Excavations revealed an enormous urban complex covering several square kilometers, including temples, theaters, fountains, aqueducts, workshops, necropolises, and public buildings. Today, Cyrene is recognized as one of the best preserved Greek cities outside Greece itself. Yet every excavation seems to uncover new mysteries. One of the first questions researchers face is simple: how did this city survive? Cyrene was established approximately 600 meters above sea level on the Jebel Akhdar plateau. Although the region receives more rainfall than much of Libya, it remains vulnerable to drought and seasonal variability. Ancient populations depended entirely on reliable water supplies. Archaeologists have identified springs, reservoirs, underground channels, and extensive distribution systems throughout the city. The most famous water source was the Spring of Apollo, which supplied fresh water to the urban centre. What continues to intrigue engineers is the precision of the hydraulic network. Water systems require carefully controlled gradients. If channels are too steep, erosion occurs. If they're too shallow, water stagnates. Modern engineers use surveying equipment capable of millimeter accuracy, yet ancient Cyrene possessed no such technology. Even so, the system functioned effectively for centuries. The mystery resembles questions surrounding Roman aqueducts, some of which maintained gradients of only a few centimeters per kilometer. In both cases, the practical knowledge behind the measurements remains only partially understood. The Temple of Zeus at Cyrene was among the largest Greek temples ever constructed. Measuring roughly 70 by 30 meters, it rivaled major sanctuaries in mainland Greece. Many of its limestone blocks weighed several tons. Today, cranes can lift such materials effortlessly, but ancient builders had only ropes, wooden frameworks, animal power, and human labor. Researchers estimate that moving a single block weighing 10 to 20 tons across uneven terrain would have required sophisticated planning and coordination. Yet construction continued on a monumental scale for generations. The same puzzle appears at the Parthenon, the temples of Sicily, and even the pyramids of Egypt. The structures survive, but the engineering manuals do not. No surviving documents explain precisely how Cyrene's builders organized transportation, lifting systems, workforce management, or construction sequencing. Only the results remain. Stretching for more than 10 kilometers around the city lies one of the largest ancient necropolises in the Mediterranean world. Thousands of tombs were carved directly into limestone hillsides. Some contain elaborate chambers, sculpted facades, and carefully engineered interiors. Creating such structures required understanding local geology. A poorly placed excavation could trigger collapses, fractures, or instability. Modern underground construction depends on geological surveys, stress analysis, and engineering calculations, yet ancient workers possessed none of these tools. Even so, many tombs have survived for over 2 millennia. Researchers still debate how ancient builders assessed rock quality and structural safety with such consistency. Of all Cyrene's mysteries, none is more extraordinary than Silphium. Unlike temples or monuments, Silphium has vanished completely. Ancient writers including Herodotus, Theophrastus, Pliny the Elder, and others describe the plant as one of the most valuable resources in the Mediterranean. Its economic importance was so immense that Cyrene placed images of Silphium on its coins for centuries. The plant became the symbol of an entire civilization. Historical records suggest Silphium was used as a medicine, spice, perfume ingredient, food additive, and possibly even a contraceptive. Pliny described it as being worth its weight in silver, and some ancient sources imply that demand extended across the Roman world. This raises a remarkable possibility. Cyrene may have controlled what was essentially an ancient biotechnology industry. Today, pharmaceutical companies invest billions of dollars searching for biologically active compounds in plants. Many modern medicines originate from natural substances. Aspirin traces its origins to willow bark, quinine emerged from cinchona trees, and artemisinin came from sweet wormwood. Silphium may represent a similar case from antiquity. The difference is that modern scientists no longer know exactly what the plant was. No confirmed specimen survives, no preserved seeds exist, and no genetic material has been recovered. Its identity remains one of archaeology's greatest biological mysteries. Some researchers believe it belonged to the Ferula genus, relatives of giant fennel and Asafoetida. Others argue that no surviving species matches ancient descriptions. Even more puzzling is the question of cultivation. Ancient authors repeatedly claimed that Silphium resisted domestication. According to historical accounts, it grew naturally only within a narrow ecological zone of Cyrenaica. Attempts to cultivate it elsewhere apparently failed. If true, this suggests an extremely specialized relationship between climate, soil chemistry, rainfall, microorganisms, and plant genetics. Modern agriculture still encounters species that are difficult or impossible to cultivate outside their native environments. Yet Cyrene managed to harvest Silphium commercially for centuries. How? Did local populations possess ecological knowledge that has been completely lost? Did they understand subtle environmental factors invisible to outsiders? Or was Silphium itself a unique biological resource unlike anything surviving today? The mystery deepens further when examining its disappearance. Ancient sources report declining populations during the Roman period. Overharvesting is often blamed. Climate change has also been proposed and habitat degradation may have contributed, yet researchers remain uncertain. Entire industries have vanished before, but few disappeared so completely that the primary biological resource itself became extinct. The loss of Silphium represents more than an economic collapse. It represents the disappearance of an entire body of biological knowledge. For this reason, some historians compare Silphium to the Antikythera mechanism. One reflects lost mechanical technology, while the other may represent lost biological technology. Both demonstrate that ancient civilizations sometimes possessed knowledge that later generations failed to preserve. Cyrene suffered numerous earthquakes throughout its history. The devastating earthquake of 365 CE struck much of the Eastern Mediterranean and caused widespread destruction. Yet portions of Cyrene survived. Some surviving structures reveal sophisticated foundations, carefully fitted masonry, and construction techniques capable of distributing loads effectively. Researchers continue investigating whether these features provided accidental seismic resistance or reflected practical engineering knowledge accumulated over centuries. The question remains unresolved. What do you think? Was silphium simply an extinct plant or evidence of biological knowledge far more advanced than we realize? Share your thoughts in the comments below. Ain Tunga, known in antiquity as Thignica, lies in northern Tunisia, approximately 70 kilometers southwest of Tunis. Today the site appears quiet and largely forgotten, overshadowed by more famous Roman cities such as Duga and Carthage. Yet beneath its ruined walls, collapsed bathhouses and weathered fortifications lies a technological mystery that continues to challenge archaeologists. The ruins reveal evidence of advanced urban planning, hydraulic engineering, large-scale construction, and military architecture. The results are visible. The methods behind them remain only partially understood. The ancient city occupied a strategic position within the fertile Majerda Valley region, one of North Africa's most productive agricultural zones. Archaeological surveys conducted during the 19th and 20th centuries reveal that Thignica was not a minor settlement. Inscriptions, public buildings, religious structures, baths, roads, and defensive works indicate a prosperous urban centre that flourished under Roman rule before later becoming a major Byzantine stronghold. What makes Ain Tunga particularly intriguing is that many of its engineering achievements seem disproportionate to the size of the city itself. One of the greatest mysteries involves the Byzantine fortress that dominates the site today. Constructed during the 6th century AD, likely under the reign of Emperor Justinian I, the fortification was part of a vast defensive network established after the Byzantine reconquest of North Africa. The fortress features massive walls, multiple towers, and a carefully planned defensive layout. Modern military engineers use satellite imagery, computer simulations, and geographic information systems to determine optimal defensive positions. Byzantine builders possessed none of these technologies. Yet the fortress occupies terrain that offers exceptional visibility across surrounding approaches and natural routes through the landscape. The question is not whether ancient engineers could build walls. They clearly could. The mystery is how surveyors consistently selected locations that maximized defensive advantages across enormous territories. Similar questions surround other military masterpieces such as the Roman forts along Hadrian's Wall and the defensive network of the Eastern Roman Empire. At Ain Tunga, the precision of site selection suggests an advanced understanding of terrain analysis that remains difficult to reconstruct from surviving evidence alone. Another puzzle concerns the transportation and reuse of construction materials. Throughout the fortress, archaeologists have identified numerous architectural elements recycled from earlier Roman buildings. Columns, capitals, blocks, and decorative stones were dismantled and incorporated into the new fortifications. Some individual stone blocks weigh several tons. Modern construction projects employ cranes, hydraulic lifting systems, and heavy machinery. Byzantine builders relied on ropes, pulleys, wooden scaffolding, rollers, and human or animal labor. Experimental archaeology has demonstrated that ancient lifting systems were remarkably effective. However, scaling such operations to the level observed at Ain Tunga remains difficult to explain in detail. The logistics required to dismantle large Roman structures, transport massive materials, and integrate them into new fortifications would have demanded extraordinary organization. The physical remains demonstrate that it happened. The precise operational methods remain uncertain. Water management presents another technological mystery. Ancient North African cities could not survive without reliable access to water. Even moderate urban populations required enormous quantities for drinking, agriculture, sanitation, fountains, workshops, and public baths. Modern estimates suggest that Roman urban residents often consumed between 100 and 500 litres of water per person per day, depending on the city and available infrastructure. Such figures rival or exceed consumption levels in some modern communities. The ruins of Unbroken indicate the presence of sophisticated hydraulic systems. Public baths, residential districts, and civic buildings all depended on continuous water supplies. Yet only fragments of the original infrastructure survive. Archaeologists have identified reservoirs, channels, and water-related installations, but much of the system has disappeared beneath centuries of erosion and reuse. This raises a fundamental question. How extensive was the original hydraulic network? Comparisons with other North African sites reveal the scale of what Roman engineers could achieve. At Carthage, aqueducts transported water across more than 130 kilometers. At Duga, carefully engineered cisterns ensured year-round supply. At Leptis Magna, hydraulic systems supported one of the largest cities in Roman Africa. Unbroken was smaller, but its surviving remains suggest that similar engineering principles were employed. The challenge is that much of the evidence has vanished, leaving researchers to reconstruct the system from isolated fragments. The city's bathhouses introduce another layer of complexity. Roman baths were among the most technologically sophisticated structures of the ancient world. They required integrated systems of plumbing, heating, ventilation, drainage, and structural engineering. Beneath many bath complexes lay hypocaust systems in which hot air circulated through hollow spaces under floors and within walls. Temperatures had to be controlled carefully to maintain separate hot, warm, and cold chambers. Modern climate control systems rely on advanced materials, sensors, and automated regulation. Roman engineers achieved similar functional goals using only masonry, geometry, airflow management, and carefully designed furnaces. At Unbroken, portions of these systems have survived, but many critical components have been lost. Researchers can identify the results, but often struggle to reconstruct the complete operational design. Urban planning itself represents one of the site's most overlooked mysteries. Ancient cities rarely developed randomly. Streets, drainage systems, public spaces, industrial zones, religious districts, and defensive structures had to function together as an integrated whole. Today, urban planners use satellite mapping, digital models, traffic simulations, and environmental analysis. Roman planners relied on surveying tools, geometry, observation, and accumulated experience. Yet the results were impressive. Across the Roman Empire, cities maintained remarkable levels of organization. Unbroken was no exception. The arrangement of public structures suggests deliberate planning rather than uncontrolled growth. The challenge for archaeologists is that the planning process itself has disappeared. No surviving blueprints explain how decisions were made. No technical manuals from the city describe surveying methods. Only the finished urban landscape remains. Perhaps the most intriguing mystery involves material science. The durability of surviving structures continues to surprise researchers. Walls, foundations, and architectural elements have endured nearly 2 millennia despite earthquakes, weathering, conflict, and abandonment. This pattern appears repeatedly throughout the ancient world. Roman concrete remains the subject of scientific research because some formulations survived marine environments for almost 2,000 years. recent studies have identified self-healing mechanisms involving lime clasts that may explain part of this durability. At Ain Tunga, builders used locally available stone combined with mortars, whose exact compositions are still being investigated. The structures demonstrate a practical understanding of materials that often exceeds expectations. Ancient craftsmen lacked laboratories, chemical analyzers, and modern engineering software. Nevertheless, they consistently produced buildings capable of surviving centuries. Sijil Massa is one of the greatest lost cities of the ancient world. Located on the edge of the Sahara Desert in southeastern Morocco, this forgotten metropolis controlled one of the richest trade networks in human history. Gold from West Africa, goods from the Mediterranean, and caravans crossing thousands of kilometers of desert all converged here. Yet the city that once accumulated immense wealth vanished almost completely, leaving behind mysteries that archaeologists still struggle to explain. The ruins of Sijil Massa lie within Morocco's Tafilalt oasis. Historical descriptions survived in medieval Arabic texts, but centuries of abandonment, erosion, flooding, and human activity erased much of the city. Modern archaeological investigations beginning in the 20th century revealed traces of urban districts, irrigation systems, workshops, and evidence of large-scale commercial activity. The discoveries confirmed that Sijil Massa was not merely a desert settlement, it was one of the most important economic centers of medieval Africa. Few locations seem less suitable for sustaining a major city than the Sahara. Average annual rainfall in the Tafilalt region is often below 100 millimeters. Summer temperatures regularly exceed 40 degrees Celsius. Water is scarce, vegetation is limited, and agricultural production faces constant environmental stress. Yet historical sources describe a prosperous city surrounded by extensive palm groves and agricultural land capable of supporting tens of thousands of people. This presents a major engineering puzzle. Modern desert cities rely on pumps, pipelines, reservoirs, electrical infrastructure, and satellite monitoring systems, but Sijil Massa possessed none of these technologies. Researchers believe its survival depended on sophisticated water management systems involving canals, diversion structures, underground channels, and carefully regulated irrigation networks. However, much of this infrastructure has disappeared. Archaeologists can identify fragments of the system, but the complete design remains unknown. How engineers maintained reliable water distribution over centuries remains one of the city's greatest mysteries. The challenge becomes even more remarkable when compared to other ancient hydraulic civilizations. The Romans constructed aqueducts capable of transporting water over distances exceeding 80 kilometers, while Persian engineers developed qanat systems that tapped underground aquifers through tunnels extending for many kilometers. Sijil Massa appears to belong within this tradition of hydraulic innovation, yet its techniques remain poorly understood. Sijil Massa served as the northern gateway of the Trans-Saharan trade network. This was not a local commercial route, it was one of the largest economic systems on Earth before the modern era. Caravans often travelled more than 1,500 kilometers through some of the harshest environments on the planet. Certain journeys required several months, and thousands of camels transported gold, ivory, salt, textiles, copper, and countless other goods between North Africa and sub-Saharan kingdoms. Maintaining such a network required extraordinary logistical planning. A camel can consume significant quantities of water and food. Human travelers required supplies, trade goods had to be protected, and navigation errors could prove fatal. Yet for centuries these routes functioned with remarkable reliability. How caravan leaders navigated vast stretches of nearly featureless desert remains debated. Some scholars point to sophisticated astronomical navigation using stars, while others suggest generations of accumulated environmental knowledge involving wind patterns, dunes, geological formations, and seasonal conditions. Whatever methods were used, the achievement rivaled the navigational abilities of Polynesian sailors crossing the Pacific Ocean without modern instruments. Historical accounts indicate that Sigil Massa became one of the wealthiest cities in North Africa. Managing such prosperity required more than merchants, it required administration. Taxes had to be collected, trade had to be regulated, agricultural production had to be monitored, water distribution had to be coordinated, and security had to be maintained. Today, such functions depend on databases, communication networks, and advanced bureaucratic systems. Sigil Massa had none of these advantages, yet records suggest that the city successfully managed commercial activity involving regions separated by thousands of kilometers. The administrative knowledge behind this achievement has largely vanished. Unlike some Roman or Chinese centers where extensive documentation survives, Sigil Massa left relatively few records explaining how its institutions functioned. As a result, historians can observe the outcome but not the mechanisms that produced it. Perhaps the most overlooked technological achievement of Sigil Massa was its ability to adapt to environmental extremes. The city existed in a region vulnerable to drought, flash floods, sand encroachment, and long-term climate fluctuations. Modern climate studies indicate that relatively small changes in precipitation can dramatically affect agricultural productivity in desert environments. Yet Sigil Massa endured for centuries. Its builders developed architectural solutions using mud brick and earthen construction. At first glance, these materials appear primitive. In reality, they possess remarkable thermal properties. Thick earthen walls absorb heat during the day and release it slowly at night, reducing temperature fluctuations inside buildings. Modern sustainable architecture increasingly studies similar principles. The challenge is understanding how builders optimize these techniques without formal engineering science. The city's longevity suggests generations of accumulated knowledge that may never be fully reconstructed. Of all Sigil Massa's technological puzzles, none may be more fascinating than its relationship with gold. For centuries, West Africa supplied an enormous proportion of the world's known gold. Medieval sources suggest that major gold-producing regions south of the Sahara generated vast quantities of the precious metal. Through its strategic location, Sigil Massa became one of the principal gateways through which this wealth entered North Africa and the Mediterranean world. Gold arriving in Sigil Massa was transformed from raw material into economic power. Archaeological evidence and historical records indicate the city played a major role in gold processing, valuation, and coin circulation. This is where the mystery begins. Producing reliable gold coinage requires far more sophistication than many people realize. Gold extracted from mines rarely possesses consistent purity. Natural gold often contains varying amounts of silver, copper, and trace elements. Without proper refinement, coins can vary significantly in value. Modern metallurgical laboratories use spectrometers, chemical analysis, and precision measurement instruments. Ancient metalworkers had none of these tools. Yet medieval Islamic gold coins achieved extraordinary commercial trust across enormous distances. Merchants in North Africa, Al-Andalus, and the Mediterranean accepted these coins because they believed their gold content was reliable. How was that trust maintained? Researchers believe skilled metallurgists employed techniques involving cupellation, alloy control, repeated melting cycles, and density-based evaluation methods. The problem is that much of the practical knowledge behind these processes was rarely documented in detail. Even today, experimental archaeologists attempting to recreate ancient refining techniques often discover that seemingly simple procedures require extensive experience and precision. Small variations in furnace temperature can alter results dramatically. Maintaining temperatures above 1000 degrees Celsius demands careful control of airflow, fuel quality, furnace geometry, and ore composition. Ancient craftsmen possessed no thermometers, yet they repeatedly achieved successful outcomes. Some historians argue that master metallurgists relied upon visual cues, flame color, sound, and centuries of transmitted expertise. If true, this would represent an extraordinarily sophisticated technological tradition largely lost to history. The scale of the operation raises additional questions. Historical estimates suggest that trans-Saharan trade moved enormous quantities of gold over many centuries. Some researchers believe that during certain periods, West African sources may have supplied a substantial portion of the gold circulating throughout the Mediterranean economy. If Sigil Massa served as a major redistribution centre, then its merchants and metal workers were effectively participating in one of the largest precious metal supply chains on Earth. Yet the infrastructure supporting this system remains only partially understood. Where were the refining workshops? How were purity standards enforced? How were fraudulent coins detected? How was gold securely stored, transported, and exchanged? The archaeological record provides fragments of answers, but not the complete picture. As a result, the metallurgical expertise of Sigil Massa remains one of the most intriguing unsolved technological mysteries of the medieval world. The greatest mystery may be not how Sigil Massa rose, but how it vanished. Political unrest, warfare, economic change, shifting trade routes, and environmental pressures likely all contributed to its decline. Like many ancient cities, it appears to have faded due to multiple factors, eventually disappearing beneath the sands. What do you think? Was Sigil Massa simply a successful trading city? Or did its inhabitants possess engineering and metallurgical knowledge far more advanced than historians currently understand? Let us know your thoughts in the comments below. Northern Tunisia. Beneath the ruins of an ordinary-looking Roman city lies one of the most extraordinary engineering mysteries of the ancient world. At Bulla Regia, wealthy residents did something almost unimaginable. Instead of building upward, they built downward. Entire luxury homes were constructed beneath the ground, complete with bedrooms, dining halls, courtyards, fountains, and some of the finest mosaics ever discovered in North Africa. Nearly 2,000 years later, archaeologists can still walk through these underground villas. What they still cannot fully explain is how ancient builders created a system so advanced that many of its engineering principles resemble modern climate-controlled architecture. Although local ruins had been known for centuries, systematic excavations began during the late 19th and early 20th centuries under French archaeologists. What they uncovered shocked researchers. Beneath the visible ruins were entire residential levels preserved underground. As excavation continued, more subterranean villas emerged, revealing a city unlike almost any other in the Roman world. Today, Bulla Regia is considered one of the best preserved examples of Roman domestic architecture ever discovered. Yet preservation is only part of the mystery. Most Roman cities followed the familiar pattern, with houses, forums, baths, and temples constructed above ground. Bulla Regia was different. Many of its elite residences included complete underground living quarters, extending several meters below the surface. At first glance, the explanation seems obvious. Tunisia experiences extremely hot summers, and modern temperatures in the region frequently exceed 40 degrees Celsius. But solving a climate problem and constructing an entire underground residential system are two very different things. Modern underground buildings require careful calculations involving thermal transfer, ventilation, structural stability, drainage, and moisture control. Ancient builders possessed no computers, no climate simulations, and no engineering software. Yet they successfully created underground spaces capable of remaining habitable for centuries. Researchers studying subterranean architecture have found that soil temperatures several meters below the surface often remain significantly more stable than air temperatures above ground. In many regions, underground temperatures fluctuate only a few degrees throughout the year. The builders of Bula Regia somehow understood this principle almost 2 millennia before modern environmental engineering. The question is how. One of the greatest mysteries involves temperature regulation. Modern architects increasingly use passive cooling systems to reduce energy consumption. Such systems rely on thermal mass, airflow, shading, and underground temperature stability. Bula Regia appears to have implemented many of these principles long before the invention of electricity. Thick stone walls absorbed heat slowly, underground chambers remained naturally cool, courtyards allowed sunlight while limiting overheating, and carefully placed openings encouraged air circulation throughout the structure. Today, these concepts are taught in architectural engineering programs. Yet no surviving Roman document explains exactly how builders at Bula Regia optimized these designs. Were they following mathematical rules? Were they relying on generations of accumulated experience? Or did they possess practical environmental knowledge that has largely disappeared from history? No one knows. Perhaps the most astonishing mystery of all lies beneath visitors' feet. The underground villas contain some of the most spectacular Roman mosaics ever discovered, and many remain remarkably intact despite spending centuries below ground. This should not have happened. Mosaics are fragile engineering systems. Each artwork consists of thousands, sometimes millions, of carefully arranged tesserae embedded within multiple layers of mortar and foundation material. For a mosaic to survive, the underlying structure must remain stable. Even minor shifts can produce cracks, moisture can weaken mortar, ground pressure can deform surfaces, and temperature changes can accelerate deterioration. Yet many mosaics at Bula Regia survived with extraordinary clarity. Some still preserve intricate mythological scenes, geometric designs, marine imagery, and detailed human figures nearly 2,000 years after their creation. The technical challenge becomes even more remarkable when considering where these mosaics were built. They were not installed in open-air courtyards. Many were placed deep underground. How did Roman craftsmen achieve such precision in enclosed subterranean spaces? Lighting presents one mystery. Modern mosaic restoration projects often require powerful artificial illumination, while ancient artisans possessed only daylight, oil lamps, and reflective surfaces. Yet the mosaics demonstrate astonishing accuracy. Another mystery involves leveling. Large mosaic floors require exceptionally flat foundations, and modern builders use laser instruments capable of measuring millimeter-scale variations. Roman craftsmen possessed none of these technologies. Nevertheless, many floors remain remarkably level after nearly 20 centuries. Then there is the problem of moisture. Underground environments naturally accumulate humidity, and water infiltration is among the greatest threats to ancient mosaics. Yet numerous examples at Bula Regia survive far better than mosaics exposed to open weather elsewhere in the Mediterranean. Some researchers believe the underground environment acted as a protective chamber, shielding the artworks from ultraviolet radiation, temperature extremes, storms, and human activity. Others argue that sophisticated drainage systems may have played a crucial role. The truth remains uncertain. What is certain is that these mosaics challenge assumptions about ancient construction capabilities. Their survival represents not merely artistic achievement, but a remarkable triumph of engineering. Any underground structure faces a fundamental problem: air. Without sufficient ventilation, carbon dioxide accumulates, humidity rises, mold spreads, and living conditions deteriorate rapidly. Yet Bulla Regia's underground residences functioned as comfortable living spaces. Archaeologists have identified courtyards, openings, stairwells, and architectural features that may have encouraged airflow. Some researchers propose that the villas exploited natural convection currents. Warm air rises while cool air sinks. If openings are carefully positioned, a building can effectively ventilate itself. Modern architects still use this principle, but determining the exact airflow behavior within Bulla Regia remains difficult because much of the original superstructure has disappeared. What survives may represent only part of a much larger system. Modern basements frequently suffer from water damage despite advanced materials and technology. Bulla Regia presents the opposite problem. Why did so many underground structures survive? Roman builders were famous for their mastery of lime mortars and hydraulic construction materials. However, the precise methods used at Bulla Regia remain uncertain. Excavations suggest careful attention to drainage, foundation preparation, and wall construction. Yet researchers still debate how these systems performed so effectively over such long periods. The question resembles ongoing investigations into Roman concrete, some of which has survived marine environments for nearly 2,000 years. Ancient builders often achieved durability that continues to surprise modern engineers. What do you think? Were the underground villas of Bulla Regia simply the product of experience? Or do they preserve forgotten engineering knowledge that has yet to be fully understood? Let us know your thoughts in the comments below. Gurvan Cave, hidden high in Mongolia's Khangai Mountains, contains paintings that may be more than 20,000 years old. The animals painted on its walls have survived longer than entire civilizations. Yet the greatest mystery is not what was painted, it is how the colors are still there at all. Gurvan Cave is located in central Mongolia, roughly 100 kilometers from the modern town of Tsetsaleg. The cave sits at an elevation of approximately 1,700 meters within the Khangai mountain region. The site became widely known to archaeologists during the 20th century when researchers documented numerous prehistoric paintings deep inside the cave. Subsequent studies identified images of ostriches, wild cattle, mountain sheep, antelope, and other animals associated with Ice Age environments. Radiocarbon analysis and stylistic comparisons suggest that some of the artwork may date back between 20,000 and 30,000 years. That age alone is remarkable, but what truly puzzles scientists is the technology hidden behind the paintings. One of the first questions concerns light. Many of the paintings are located far beyond the reach of natural sunlight. Even today, entering the deeper chambers requires artificial illumination, and for prehistoric artists, this presented a major engineering challenge. Producing artwork inside a dark cave is not as simple as carrying a burning torch. Torches create smoke, consume oxygen, and produce unstable flickering light. Over long periods, soot can accumulate on cave walls and damage artwork. Experimental archaeology has demonstrated that prehistoric cave artists in Europe often relied on stone lamps fueled by animal fat. These lamps generated steadier light while producing less smoke than open flames. Whether the artists of Gurvan used similar technology remains uncertain. The mystery is not merely artistic, but also logistical. How did people without metal tools, electricity, or written instructions maintain sufficient illumination to create detailed paintings deep underground? The answer remains unknown. Of all the unanswered questions surrounding Gurvan Cave, none may be more fascinating than the survival of its pigments. At first glance, prehistoric paint appears simple. Researchers believe the artists primarily used natural mineral pigments, especially red ochre rich in iron oxides. Yet minerals alone do not explain the extraordinary durability of the artwork. Modern paints require binders, stabilizers, and carefully controlled chemical compositions to maintain adhesion. Without these elements, pigments gradually flake away, dissolve, or detach from surfaces. The paintings of Gervin Senker have survived for tens of thousands of years, and that fact raises a profound technological mystery. What exactly did the artist mix with the pigments? Researchers have proposed several possibilities. Animal fat may have acted as a binding agent, blood could have contributed proteins that improved adhesion, and plant resins may have helped protect surfaces. Some scholars have suggested combinations of multiple organic substances. The problem is that most organic materials decompose over thousands of years, leaving little evidence behind. As a result, scientists can identify many of the mineral components, but often struggle to reconstruct the complete original formula. This challenge is not unique to Mongolia. At the famous Lascaux cave in France, pigments have survived for approximately 17,000 years. At Chauvet Cave, some paintings exceed 30,000 years in age. At Altamira Cave, colours remain vivid after more than 14,000 years. Yet despite decades of research, scientists still debate the exact preparation techniques employed by prehistoric artists. Gervin Senker belongs to the same category of mystery. The paintings suggest a level of material knowledge far beyond what many people associate with Ice Age hunter-gatherers. Ancient artists may have understood through generations of experimentation which minerals produced stable colours, which organic substances enhanced durability, and which cave surfaces preserved artwork most effectively. If so, they possessed a form of practical chemistry thousands of years before formal science existed. Another overlooked mystery involves the rock itself. Not every surface inside a cave is suitable for painting. Moisture can destroy pigments, salt crystals can cause flaking, and temperature fluctuations can accelerate deterioration. The artists appear to have selected specific sections of the cave where preservation conditions were unusually favourable. This decision may not have been accidental. Modern conservation studies show that microclimate conditions can dramatically influence the survival of pigments. Differences of only a few degrees Celsius or slight changes in humidity can determine whether artwork survives for centuries or disappears entirely. How did prehistoric people identify the most stable surfaces? Were they simply lucky, or did generations of observation teach them which areas offered the greatest long-term preservation? The evidence cannot yet provide a definitive answer. The paintings themselves are impressive, but the knowledge behind them may be even more extraordinary. To create durable cave art, prehistoric communities needed to master several independent skills. They had to locate pigment sources, process minerals into usable powders, identify suitable binding agents, prepare rock surfaces, produce reliable lighting systems, and pass this knowledge from one generation to the next. Yet no manuals survive. No written records exist. No technical instructions remain. Only the final product has endured. This creates a paradox familiar throughout archaeology. The evidence proves that the knowledge existed, but the knowledge itself has disappeared. The unanswered questions surrounding Gervin Senker resemble mysteries found throughout the ancient world. The builders of the Great Pyramid of Giza achieved astonishing precision despite lacking modern machinery. The creators of the Antikythera mechanism constructed a mechanical calculator more than 2,000 years ago. Roman engineers developed concrete formulations that continue attracting scientific attention nearly 2 millennia later. In every case, researchers can study the results but only partially reconstruct the process. Gervin Senker presents the same challenge. Scientists can analyze pigments using spectroscopy, map cave environments with laser scanners, and examine microscopic paint particles using electron microscopes. Yet some of the most important questions remain unanswered. What ingredients were mixed together? How were formulas developed? How were techniques transmitted across generations? And why have some paintings survived for over 20 millennia while countless others vanished forever? What do you think? Were these paintings preserved mainly because of the cave's unique environment? Or did Ice Age artists possess sophisticated material knowledge that we still do not completely understand? Let us know your thoughts in the comments below. Northern Tunisia, approximately 110 kilometers southwest of Tunis, is home to Douga, a city that stands on a hill overlooking fertile valleys that once supported one of North Africa's most prosperous ancient urban centres. Archaeological investigations began during the 19th century, and extensive excavations throughout the 20th century revealed an astonishingly preserved urban landscape covering roughly 75 hectares. Today, Douga is recognized as one of the best preserved Roman cities anywhere in the world. Yet beneath its temples, theatres, bathhouses and streets lies a collection of technological mysteries that continue to challenge archaeologists, engineers and historians. The ruins reveal what ancient builders achieved. What remains uncertain is exactly how they achieved it. The first mystery appears immediately when viewing the city from above. Most Roman cities were designed according to standardized urban planning principles. Engineers preferred relatively flat terrain where roads could follow orderly grid patterns. Douga is different. The city occupies a steep hillside with significant elevation changes. Modern urban planners working on a similar site would rely on satellite imagery, digital elevation models, laser scanning, GPS surveys, and computer simulations. The builders of Douga possessed none of these technologies. Nevertheless, they successfully integrated public squares, residential districts, water infrastructure, temples, markets, bath complexes, and administrative buildings into an extremely challenging landscape. The question is not whether they succeeded. The ruins prove that they did. The mystery is how ancient surveyors achieved such precision. Even small errors in elevation measurements can create enormous problems for drainage systems, building foundations, and transportation routes. Yet Douga functioned successfully for centuries. Researchers have reconstructed parts of the city's layout and repeatedly concluded that its planning required a sophisticated understanding of topography. The exact surveying methods used by local engineers remain only partially understood. Closely connected to this mystery is the city's remarkable water management system. Water represented the foundation of every successful Roman settlement. Without reliable access to water, urban populations could not survive. Douga developed an extensive network of reservoirs, cisterns, channels, fountains, and drainage systems capable of supporting thousands of inhabitants. Modern hydraulic engineers use computer modeling to predict flow rates, pressure changes, storage capacity, and seasonal fluctuations. Ancient builders relied on observation, geometry, and accumulated practical knowledge. Yet the hydraulic performance achieved at Douga remains impressive even by modern standards. Archaeologists have identified massive storage installations capable of collecting and distributing water across different sections of the city. These systems required precise gradients. A channel that is too steep causes erosion and instability. A channel that is too shallow fails to move water effectively. The famous Roman aqueducts provide useful comparisons. The Aqua Claudia near Rome maintained an average gradient of only a few meters per kilometer across enormous distances. Similar principles appear throughout Douga's infrastructure. The challenge becomes even greater because the city occupies uneven terrain. Researchers can measure the surviving structures, but they still debate how ancient engineers calculated and maintained such accuracy without modern instruments. Another mystery concerns construction logistics. Duga contains monumental buildings constructed from enormous stone blocks weighing several tons. The capital, completed during the 2nd century AD, remains one of the finest examples of Roman architecture in Africa. Massive columns, heavy stone elements, and precisely fitted masonry continue to dominate the site. Modern construction companies use cranes, hydraulic lifting systems, reinforced vehicles, and advanced engineering software to move comparable materials. Ancient builders possessed ropes, pulleys, wooden cranes, animal power, and human labor. Historical sources confirm that Roman engineers developed sophisticated lifting technologies. Archaeological evidence from across the empire demonstrates remarkable mechanical capabilities. However, many details remain uncertain. Researchers estimate that some Roman cranes could lift several tons under ideal conditions. Yet transporting large stone blocks uphill across rugged terrain introduces additional complications. Similar questions arise at other famous archaeological sites. The Great Pyramid of Giza contains stone blocks weighing up to 80 tons in some internal chambers. The builders of Baalbek moved megaliths weighing hundreds of tons. Duga belongs to the same category of ancient logistical puzzles. The structures survive. The exact sequence of operations used to construct them often does not. The durability of Duga presents another engineering mystery. Many structures have survived nearly 2,000 years despite exposure to weather, seismic activity, temperature fluctuations, biological growth, and erosion. This longevity becomes particularly impressive when compared to many modern buildings that require major repairs after only a few decades. Scientists studying ancient construction materials frequently encounter unexpected results. Roman concrete has become famous because some marine structures survived for almost 2 millennia. Recent analyses suggest that self-healing chemical reactions contributed to this durability. Duga raises similar questions. Mortars, stone joints, foundations, and construction techniques demonstrate extraordinary resilience. Researchers continue investigating why certain ancient materials perform so effectively. The builders clearly understood load distribution, structural stability, and environmental adaptation. Yet many technical details remain uncertain because the craftsmen left few written explanations. Modern engineers can analyze the materials chemically, but reconstructing the complete manufacturing process remains difficult. Perhaps the most overlooked mystery involves thermal engineering. Summers in northern Tunisia can be extremely hot. Maintaining comfortable indoor temperatures without electricity represents a major challenge. Nevertheless, Duga's architects designed buildings that functioned efficiently within the local climate. Many structures exhibit evidence of passive cooling strategies. Building orientation, wall thickness, airflow management, shaded spaces, and urban layout all appear carefully considered. Today, architects use computer simulations to optimize thermal performance. Ancient builders relied entirely on experience and observation. Some researchers have suggested that Roman and pre-Roman architects possessed a practical understanding of environmental engineering far more sophisticated than often assumed. Similar patterns appear in ancient cities throughout the Mediterranean, from Petra in Jordan to settlements across North Africa. Duga provides another example of ancient builders achieving impressive environmental control without modern technology. The theatre of Duga introduces yet another puzzle. Constructed during the reign of Emperor Marcus Aurelius around AD 168 or 169, the theatre could accommodate approximately 3,500 spectators. Its location takes advantage of the natural hillside, reducing construction requirements while enhancing visibility. What fascinates modern researchers is acoustics. Even today, many Roman theatres demonstrate remarkable sound transmission. Computer models reveal that architectural geometry often contributes significantly to acoustic performance. Whether ancient architects fully understood the physics involved remains uncertain. Modern concert halls require detailed acoustic simulations. Roman builders obviously lacked such tools, yet many theatres consistently achieve results that surprise contemporary engineers. Duga's theatre joins a long list of ancient structures where performance appears to exceed expectations based solely on trial and error. Beyond individual technologies lies a larger mystery involving cultural knowledge transfer. Duga was not originally a Roman city. Before Roman domination, the settlement belonged to the Numidian world and maintained strong connections with Punic traditions originating from Carthage. Over centuries, indigenous, Punic, and Roman influences blended together. This creates a significant challenge for historians. Which technologies originated locally? Which arrived from Carthage? Which were introduced by Roman engineers? The archaeological evidence often reveals the final result but not the path by which knowledge developed. Many historians increasingly view ancient technological progress as a process of cultural exchange rather than isolated invention. Duga may represent one of the best examples of this phenomenon. The city appears to preserve engineering traditions accumulated over generations and across multiple civilizations. Western Armenia's Arashrat plain near the banks of the Aras River hides the ruins of Argishti Kinili, an Iron Age city built nearly 2,800 years ago. Beneath its collapsed walls lies evidence of engineering, metallurgy, and logistical capabilities that researchers still struggle to fully explain. Argishti Kinili was first identified through archaeological investigations during the 20th century after inscriptions of King Argishti had revealed the existence of a major Eurasian administrative centre. Excavations uncovered fortifications, granaries, irrigation systems, workshops, and thousands of artifacts that transformed the understanding of the ancient kingdom of Urartu. One of the first mysteries surrounding Argishti Kinili is the speed at which it seems to have emerged. Historical inscriptions suggest that the city was founded during the reign of Argishti I, around 776 BCE. Unlike settlements that evolved gradually over centuries, Argishti Kinili appears to have been planned from the beginning. Archaeological surveys reveal organized districts, defensive structures, storage facilities, administrative areas, and industrial zones integrated into a coherent urban plan. This immediately raises questions because planning a city requires accurate knowledge of terrain, water supply, transportation routes, population requirements, and military strategy. Modern urban planners rely on satellite imagery, topographic surveys, and digital modeling software, yet the builders of Argishti Kinili possessed none of these tools. Even so, the city functioned as a highly organized administrative machine, and researchers continue debating how Eurasian engineers measured, mapped, and coordinated such large-scale construction projects with remarkable precision. Perhaps the most visible technological achievement of Urartu was water management. The Ararat Plain experiences hot summers and relatively limited rainfall, making large-scale agriculture dependent on artificial irrigation. Excavations throughout former Eurasian territory have revealed canals extending for dozens of kilometers, and some channels maintained gradients so precise that water could flow efficiently across long distances without causing erosion or stagnation. Even today, irrigation engineers understand that extremely small errors in slope calculations can cause major failures. A canal descending too rapidly destroys its own banks, while a canal descending too slowly may stop flowing altogether. The challenge becomes even greater over distances exceeding 20 or 30 kilometers. Archaeological depended on this hydraulic infrastructure, and the mystery is not whether the canals worked, because archaeological evidence proves they did. The real mystery is how surveyors achieved such accuracy without modern instruments. Some scholars compare Eurasian hydraulic achievements to the Roman aqueducts that would appear centuries later, while others suggest that the kingdom developed surveying techniques that were largely lost after its collapse. Of all the technological puzzles associated with archaeological, none may be more fascinating than metallurgy. The kingdom of Urartu was famous throughout the ancient Near East for its metalworking, and Assyrian records frequently described Eurasian wealth in terms of metals, weapons, armor, and crafted objects. Archaeological excavations have uncovered iron tools, bronze artifacts, weapons, slag deposits, furnace remains, and evidence of large-scale metal production. At first glance, ancient metallurgy may seem simple. In reality, it represents one of the most difficult technological challenges ever mastered by early civilizations. Producing useful iron requires temperatures approaching 1,200 degrees Celsius or higher, and maintaining such temperatures demands precise control of airflow, fuel quality, furnace design, and ore composition. A furnace that receives too little oxygen cannot reach sufficient temperatures, while a furnace that receives too much oxygen may consume fuel inefficiently or damage the metal being produced. The astonishing fact is that Eurasian metalworkers achieved consistency. Thousands of artifacts recovered from Eurasian sites demonstrate standardized production methods rather than occasional experimentation, suggesting generations of accumulated technical knowledge. Yet almost none of that knowledge survives. No Eurasian metallurgical manuals have been discovered, no engineering texts explain furnace construction, and no technical diagrams reveal how airflow was regulated. Modern experimental archaeologists attempting to recreate ancient iron production often discover that seemingly simple furnaces hide extraordinarily complex engineering principles. Airflow patterns inside a furnace can determine whether iron forms successfully or fails entirely, and even minor differences in furnace geometry can dramatically affect efficiency. Researchers studying ancient slag have found evidence that some Iron Age metallurgists understood these relationships remarkably well despite lacking modern chemistry. The mystery becomes even greater when bronze production is considered. Bronze requires carefully controlled ratios of copper and tin, and both materials often originated from different locations. This means Eurasian craftsmen not only mastered metallurgy, but also maintained supply networks capable of delivering essential raw materials over significant distances. Comparisons with other ancient civilizations make the puzzle even more intriguing. The famous ironworking traditions of the Hittites remain partially understood. The metallurgical achievements of ancient Africa continue surprising researchers today, and Roman metallurgy reached industrial scales that were once thought impossible for the ancient world. Urartu belongs within this same category of technological excellence. The difference is that far less documentation survives. As a result, historians can see the product but not the complete process. The machines vanished, the engineers vanished, and only the results remain. Archaeological also demonstrates remarkable defensive engineering. The city occupied strategically advantageous terrain overlooking critical transportation routes, and its walls were designed not merely as barriers but as integrated military systems. Construction required moving enormous quantities of stone and earth. Without cranes, engines, or mechanized transportation, laborers somehow assembled fortifications capable of surviving for millennia. Many ancient defensive structures eventually collapsed entirely, yet portions of Archaeological foundations remain recognizable after nearly 28 centuries. This durability suggests a sophisticated understanding of structural stability, load distribution, and construction techniques. How much of this knowledge was based on formal engineering principles and how much derived from experience remains uncertain. Excavations uncovered massive storage facilities capable of holding huge quantities of grain. These installations were essential for supporting armies, administrators, craftsmen, and local populations. Ancient grain storage was far more complicated than simply filling containers, as moisture, insects, fungi, rodents, and temperature fluctuations constantly threatened supplies. Even modern storage facilities require careful environmental management. Yet many ancient societies successfully preserved food for extended periods. Archaeological appears to have operated on a scale suggesting advanced logistical planning, and researchers continue investigating how airflow, architecture, and storage design may have helped protect vital resources. Perhaps the greatest mystery of Archaeological is the knowledge that no longer exists. Before constructing canals, walls, roads, workshops, and administrative buildings, engineers needed accurate measurements. They needed to understand gradients, calculate distances, and align structures across complex terrain. Today, such work depends on laser scanners, GPS receivers, drones, and digital mapping systems. The builders of Archaeological possessed none of these technologies, yet the archaeological record demonstrates results that required impressive precision. Mactaris is one of the most overlooked archaeological mysteries in North Africa. Located in modern-day northwestern Tunisia, approximately 140 kilometers southwest of Tunis and nearly 900 meters above sea level, the ancient city sits on a rocky plateau where water is limited. Winters can be harsh, and construction conditions are far from ideal. Yet, for centuries, Mactaris flourished as a major urban centre. Today, its ruins reveal evidence of sophisticated engineering, urban planning, hydraulic technology, and construction techniques that continue to raise questions among archaeologists and historians. Unlike the Great Pyramid of Giza, which is famous for a single monumental achievement, Mactaris presents a different mystery. The entire city appears to have functioned as a complex technological system. Roads, reservoirs, public buildings, temples, workshops, and residential districts work together in a way that suggests advanced practical knowledge. The problem is that very little documentation survives to explain how this knowledge was acquired, transmitted, or applied. The site was first documented by European explorers and scholars during the 19th century. Systematic archaeological investigations throughout the 20th century gradually revealed a city whose history stretched from the Numidian period into the Roman era. Excavations uncovered temples, baths, forums, triumphal structures, water installations, and one of the most remarkable monuments in North Africa, the Scola Juvenum, a large building associated with a youth organization that still preserves inscriptions and architectural details. Yet, despite more than a century of research, many aspects of the city's engineering remain only partially understood. The first major mystery concerns water. Mactaris was built on elevated terrain without access to a major river. Modern cities facing similar conditions depend on pumps, reservoirs, treatment plants, and computerized management systems. Ancient Mactaris had none of these advantages. Nevertheless, archaeological evidence reveals an extensive network of cisterns, channels, collection systems, and storage facilities capable of supporting thousands of residents. Researchers estimate that public baths alone could consume tens of thousands of litres of water every day. Roman baths elsewhere in the empire often required between 20,000 and 100,000 litres daily depending on size. Maintaining such facilities on a high plateau required careful planning. Rainwater harvesting appears to have played a major role, but many details remain uncertain. How were storage capacities calculated? How did engineers predict seasonal shortages? How were losses from evaporation minimized? Some reservoirs survived for nearly 2 millennia, suggesting a level of hydraulic expertise that rivals many pre-industrial societies. The challenge becomes even more impressive when compared to other ancient hydraulic systems. Petra in modern Jordan developed complex water channels to survive in the desert. Roman aqueducts transported water across hundreds of kilometers. The Nabateans mastered water conservation in arid environments. Maktaris belongs within this tradition, yet unlike Petra or Rome, it lacked a large-scale aqueduct network supplying a constant flow of water. Its survival depended on managing limited resources with extraordinary efficiency. The second mystery involves stoneworking and construction. Throughout the site, enormous stone blocks were cut, transported, and assembled with remarkable precision. Some structures remained standing despite centuries of earthquakes, erosion, and human activity. Modern engineers studying ancient construction often emphasize the logistical challenges rather than the cutting itself. A stone block weighing 10 or 20 tons is not impossible to carve. The real challenge is moving it across uneven terrain without cranes, trucks, hydraulic lifts, or modern machinery. Experimental archaeology has demonstrated that ancient workers could move heavy stones using ropes, sledges, rollers, and manpower. However, scaling such methods to the level observed at Maktaris raises difficult questions. Large public buildings required hundreds or even thousands of tons of stone. Quarries supplied material over extended periods. Transport routes had to remain functional. Construction schedules had to be coordinated. The city effectively operated a long-term industrial system centuries before the Industrial Revolution. This leads directly to another mystery: organization. Modern infrastructure projects rely on managers, engineers, logistics specialists, architects, surveyors, accountants, and supply chains. Maktaris clearly required similar functions, yet little evidence survives regarding how such operations were administered. No engineering manuals have been discovered. No construction blueprints survive. No detailed descriptions explain how labor was coordinated. The city itself proves the system existed, but the mechanisms behind it remain largely invisible. One of the most intriguing questions involves surveying technology. Before construction could begin, builders needed accurate measurements. Roads had to align with public spaces. Buildings required stable foundations. Drainage systems depended on carefully controlled gradients. Today, such tasks are performed using GPS receivers, laser scanners, drones, satellite imagery, and digital modeling software. Ancient surveyors relied on simple instruments, geometry, and observation. Yet the results often display surprising precision. Across the Roman world, engineers regularly achieved alignments accurate to within fractions of a degree. Similar achievements can be seen in Roman roads, aqueducts, and military camps. Maktaris demonstrates the same pattern. The city appears carefully planned despite being built on irregular terrain. How ancient surveyors achieved this consistency remains a subject of ongoing study. Another mystery concerns material science. Many structures at Maktaris survived nearly 2,000 years of environmental exposure. Temperature fluctuations, seasonal rainfall, wind erosion, biological growth, and human activity normally destroy ancient buildings over long periods. Yet substantial portions of the city remain recognizable. The durability of ancient construction materials continues to surprise researchers worldwide. Roman concrete, for example, has survived marine environments for nearly 2,000 years and remains the subject of scientific investigation. Studies have shown that certain Roman concretes developed self-healing properties through chemical reactions involving limeclasts. Similar questions arise at Maktaris. What mortars were used? How were they formulated? Did local craftsmen possess specialized knowledge of aggregates, binders, and stone selection that has since been lost? The answer may never be fully known because ancient builders rarely documented their methods in ways that survived. Archaeologists can analyze chemical compositions, microscopic structures, and construction techniques, but reconstructing the complete technological process remains difficult. Perhaps the most fascinating mystery is the relationship between Numidian and Roman engineering. Mactaris existed before becoming fully integrated into the Roman world. The city developed within a region influenced by indigenous North African traditions long before Roman administration arrived. As a result, archaeologists continue debating which technological achievements originated locally and which were introduced from elsewhere. This question has broader implications. Traditional historical narratives often portray advanced engineering as something that flowed outward from major imperial centers. However, evidence from North Africa increasingly suggests a more complex reality. Indigenous societies possess their own expertise in construction, water management, agriculture, and urban organization. Mactaris may represent a fusion of Numidian and Roman knowledge rather than a simple transfer of technology in one direction. Cella is not supposed to be one of the greatest engineering mysteries of the ancient world. Unlike the pyramids of Egypt or the massive stones of Baalbek, its ruins appear modest at first glance. Yet beneath the walls of this forgotten city near Rabat, Morocco, archaeologists have uncovered evidence of sophisticated hydraulic systems, advanced urban planning, durable construction techniques, and layers of civilization stacked upon one another for more than 2,000 years. The deeper researchers dig into Cella, the more they encounter a troubling question. How much of the technical knowledge that built this city has been lost forever? Located on the southern bank of the Bou Regreg River, Cella occupies a strategic position overlooking one of the most important waterways on Morocco's Atlantic coast. The site was first occupied by the indigenous Mauritanian population centuries before Roman rule. During the 1st century AD, the Romans transformed it into Sala Colonia, one of the westernmost cities of the Roman Empire. After the Roman withdrawal, the city declined, only to be revived centuries later by the Marinid dynasty, which converted the site into a royal necropolis during the 14th century. Archaeological investigations conducted throughout the 20th century revealed that Cella was not a single city, but a complex accumulation of civilizations layered one atop another. Every excavation exposed new structures, new foundations, and new mysteries hidden beneath earlier occupations. One of the greatest enigmas of Cella is its water management system. Today, the region experiences long dry seasons and irregular rainfall, conditions that make water control essential for survival. Yet excavations have revealed a remarkably complex network of wells, underground channels, reservoirs, drainage systems, and storage basins distributed throughout the site. Even more remarkable is the fact that some components continued functioning for centuries after their construction. Modern engineers studying ancient hydraulic systems often compare Roman water management to a form of low-tech engineering genius. Unlike modern cities equipped with electric pumps, sensors, and computerized controls, Roman systems depended entirely on gravity, gradients, and precise calculations. At Cella, builders had to transport, store, and distribute water efficiently across uneven terrain without any modern surveying equipment. The exact methods used to calculate flow rates, pressure distribution, and seasonal supply remain largely unknown. Similar mysteries surround Roman hydraulic systems at Pompeii, Leptis Magna, and Volubilis, but Cella presents an especially challenging case because multiple civilizations modified the system over centuries, making it difficult to determine which innovations belong to which period. Equally mysterious is the city's urban planning. Satellite surveys and archaeological mapping reveal a surprisingly organized layout. Roads, residential areas, public spaces, and administrative structures were positioned according to carefully planned principles rather than random expansion. Such planning required extensive surveying long before construction began. Today, engineers use GPS satellites, laser scanners, and digital mapping software to achieve this level of precision. Roman surveyors possessed none of these technologies. Instead, they relied on simple instruments such as the groma and chorobates. Yet, despite these limitations, Roman cities throughout the empire often maintained astonishing geometric accuracy. At Cella, some alignments remained so precise that archaeologists continue debating whether they were purely practical or incorporated astronomical observations. The challenge is understanding how surveyors operating on the empire's distant frontier achieved standards comparable to those found in major Roman centers thousands of kilometers away. The durability of Cella's structures presents another technological puzzle. The site has endured earthquakes, seasonal flooding, temperature fluctuations, erosion, and centuries of abandonment. Nevertheless, significant sections of walls, foundations, gates, and public buildings remain standing. Material analysis shows extensive use of local stone combined with sophisticated mortar mixtures. Recent studies of Roman concrete elsewhere in the Mediterranean have revealed that ancient builders sometimes created materials capable of self-repair through chemical reactions involving lime clasts and seawater. Although Cella's construction differs from coastal Roman harbours, researchers continue investigating whether similar chemical mechanisms contributed to its longevity. What is certain is that many ancient structures have survived longer than comparable modern concrete constructions. Understanding exactly why remains one of archaeology's most important engineering questions. Perhaps the most overlooked mystery concerns the transfer of technical knowledge. Sala Colonia existed at the extreme western edge of the Roman world, thousands of kilometers from Rome itself. Yet the city possessed infrastructure, architectural standards, and construction methods consistent with those used throughout the empire. This suggests the existence of highly effective systems for transmitting engineering knowledge across vast distances. Modern corporations depend on digital communication networks to coordinate projects internationally. Roman engineers relied on handwritten documents, personal travel, and apprenticeship systems. How detailed were the plans sent to provincial builders? How were standards maintained? How were complex construction techniques taught and reproduced across continents? The surviving evidence provides only fragments of the answers. The site also raises questions about environmental engineering. The Buru Greg estuary is a dynamic environment influenced by tides, sediment deposition, seasonal flooding, and changing river channels. Settlements established too close to unstable waterways often face long-term sustainability problems. Yet Cella remained occupied for centuries. This longevity suggests that its inhabitants possessed a sophisticated understanding of local environmental conditions. Archaeological evidence indicates deliberate management of drainage systems and careful positioning of critical structures. Some researchers believe the city's planners actively adapted to changing hydrological conditions over generations. If true, this would place Cella among a growing number of ancient sites demonstrating environmental engineering capabilities often underestimated by modern observers. Another mystery involves the repeated rebuilding of the site. Excavations reveal that successive populations frequently constructed new buildings directly atop older foundations. In some areas, Roman structures reused earlier Mauritanian elements, while Marinid builders later incorporated Roman remains into their own architecture. This process created an extraordinarily complex archaeological record. Yet it also suggests that later builders recognized the value of earlier engineering works. Foundations, walls, drainage channels, and water systems were often preserved rather than completely replaced. Why? One possibility is that ancient engineers recognized the exceptional quality of previous construction. Another is that they no longer fully understood how to reproduce certain techniques, and therefore chose to reuse what already existed. Similar patterns can be observed at cities such as Ephesus, Athens, and Jerusalem, where successive civilizations inherited and adapted infrastructure built by their predecessors. The Marinid phase of Cella introduces another layer of mystery. During the 14th century, the site became a royal necropolis enclosed by massive walls. These fortifications remain among the most impressive surviving structures at the site, built using traditional Moroccan techniques. They demonstrate remarkable durability despite centuries of exposure. Archaeologists continue studying the composition of the construction materials and the engineering methods used to stabilize such extensive defensive works. Although less technologically advanced than Roman concrete, the walls represent a different tradition of engineering knowledge whose details are still being investigated. Modern archaeological technologies have only deepened the mystery. Ground-penetrating radar, geophysical surveys, and remote sensing have identified anomalies beneath the surface that may represent undiscovered buildings, buried infrastructure, or earlier occupation layers. Large portions of the site remain unexcavated. Every new investigation reveals additional complexity rather than providing definitive answers. Instead of simplifying the story of Cella, modern science has shown that the city was far more technologically sophisticated than previously believed. Tidis rises from a steep mountainside in northeastern Algeria, approximately 30 kilometers northwest of Constantine. Unlike the vast Roman cities built across open plains, Tidis was constructed directly into rugged, limestone terrain, where every street, staircase, reservoir, and building had to be adapted to a landscape that seemed fundamentally unsuitable for urban development. Today, the ruins appear modest compared to famous sites such as Pompeii or Leptis Magna. Yet beneath the weathered stones lies one of North Africa's most overlooked engineering mysteries. Archaeologists have spent decades studying Tidis, and the more they uncover, the more difficult questions emerge. How did ancient builders transform a mountainside into a functioning city without modern surveying equipment? How did they manage water in a semi-arid environment? And how did they carve, transport, and assemble enormous quantities of stone using technologies that should have imposed severe limitations? The modern rediscovery of Tidis began during French archaeological investigations in the 20th century. Excavations gradually revealed a settlement occupied during the Numidian period and later expanded under Roman rule. Researchers uncovered houses, temples, streets, reservoirs, workshops, defensive structures, and extensive rock-cut infrastructure. What initially appeared to be a relatively ordinary provincial city soon revealed characteristics that distinguished it from nearly every other Roman settlement in North Africa. Unlike cities designed on flat terrain according to the familiar Roman grid pattern, Tidis was forced to adapt to steep gradients, irregular rock formations, and limited access routes. Every aspect of its construction required solutions to engineering problems that remain only partially understood. The first mystery begins with the city's location itself. Modern engineers generally avoid building large urban centres on terrain as difficult as that found at Tidis. Steep slopes increase construction costs, complicate transportation, and create long-term stability challenges. Today, engineers rely on GPS systems, laser scanning, computer modelling, and geological analysis before undertaking major mountain construction projects. The builders of Tidis possessed none of these technologies. Nevertheless, they successfully established a city that functioned for centuries. The arrangement of roads, residential districts, public buildings, and defensive structures suggests careful planning rather than random growth. Archaeologists can see the final result, but the methods used to design and survey the site remain largely unknown. Particularly intriguing is the precision with which the builders adapted architecture to the terrain. Streets wind along contours that maximize accessibility while minimizing excessive gradients. Buildings were positioned to take advantage of natural rock platforms. In several areas, entire sections of the mountain were reshaped to accommodate urban expansion. Such modifications required detailed knowledge of topography and structural stability. Modern surveying instruments can measure elevation differences with millimeter precision. Ancient engineers relied on simple tools, geometry, and accumulated experience. Yet the effectiveness of their solutions continues to impress researchers. The second mystery involves the enormous amount of rock removal required to create the city. Throughout Tidis, staircases, pathways, foundations, drainage channels, and building platforms were carved directly into the bedrock. Visitors can still see extensive evidence of excavation performed nearly 2,000 years ago. Modern quarrying operations depend on powered machinery capable of removing hundreds of tons of stone per day. Ancient workers possessed only hand tools made from iron and steel. Estimating the labor involved reveals a staggering challenge. Experimental archaeology has shown that cutting limestone with ancient tools is an extremely slow process. Depending on the hardness of the rock, removing a single cubic meter can require dozens or even hundreds of labor hours. Across Tidis, thousands of cubic meters were modified. This raises difficult questions. How many workers participated? How long did construction take? How was labor organized and supervised? Where was the excavated material transported? No surviving records provide definitive answers. The city demonstrates results that required extraordinary effort, yet the logistical systems behind those achievements remain largely invisible. The third mystery concerns water. Tidis occupied a mountainous environment within a region characterized by seasonal rainfall and long dry periods. Sustaining an urban population under such conditions required sophisticated water management. Archaeological excavations have uncovered reservoirs, cisterns, collection systems, and channels designed to capture and store precious water supplies. These installations reveal a remarkable understanding of hydrology. Water engineering represented one of the greatest achievements of ancient civilizations. The Romans built aqueducts stretching hundreds of kilometers. Petra developed systems capable of supporting urban life within an arid desert environment. Machu Picchu integrated drainage networks into a steep mountain landscape. Tidis belongs within this tradition. Yet, important questions remain unanswered. Researchers still debate the full capacity of the city's water infrastructure and the efficiency of its distribution systems. Some estimates suggest that carefully designed storage facilities could have provided significant reserves during dry seasons. However, the precise operating principles of the entire network remain incompletely reconstructed. Equally impressive is the evidence for drainage engineering. Mountain settlements face constant threats from erosion and flash flooding. Heavy rains can destabilize foundations and destroy infrastructure. The continued survival of many structures at Tidis suggests that its builders understood how to control runoff and protect vulnerable areas. Similar principles are employed by modern civil engineers when designing mountain communities. The fact that ancient builders achieved comparable results using far simpler technology remains remarkable. Another mystery involves the construction materials themselves. Many walls at Tidis have survived centuries of exposure to temperature fluctuations, rain, wind, and seismic activity. Ancient builders relied on mortars, stoneworking techniques, and construction methods that continue attracting scientific interest throughout the Roman world. Research into Roman concrete has revealed self-healing mineral reactions capable of increasing durability over time. Some Roman harbour structures have survived nearly 2,000 years in marine environments. Tidis presents a related puzzle. While the site does not possess the massive concrete monuments found elsewhere in the empire, many surviving structures demonstrate durability exceeding what might be expected from their age and environmental exposure. Material scientists continue studying ancient mortars and masonry techniques across North Africa to understand how such longevity was achieved. The exact formulations used at individual sites often remain uncertain because written technical manuals rarely survived. The city's defensive design introduces another engineering enigma. Tidis occupied a naturally strategic position overlooking surrounding terrain. Builders integrated fortifications into the mountain itself, exploiting cliffs, steep slopes, and narrow access routes. Modern military planners recognize elevation as one of the most valuable defensive advantages. Ancient engineers clearly understood the same principle. By combining architecture with geography, they transformed the landscape into a defensive system. What remains unclear is the extent to which these defenses were planned from the beginning. Some researchers suggest gradual expansion over generations. Others argue that the city's layout reflects a coherent strategy developed by experienced planners. Determining which interpretation is correct remains difficult because the archaeological record preserves structures but not the decision-making processes behind them. Perhaps the most fascinating mystery concerns the transfer of knowledge between the Numidian and Roman worlds. Tidis existed at the intersection of two technological traditions. Numidian populations occupied the region before Roman expansion, while Roman administration later introduced new architectural styles, engineering practices, and urban institutions. Archaeologists often struggle to distinguish which innovations originated locally and which were imported. This question extends far beyond Tidis itself. Across the ancient Mediterranean, technological exchange shaped the development of civilizations. Roman engineers learned from Greek mathematics, Egyptian surveying, and Near Eastern hydraulic systems. Local populations adapted imported technologies to regional conditions. Tidis may preserve evidence of similar processes, but many details remain uncertain. Some solutions attributed to Roman engineering may have incorporated indigenous knowledge accumulated over centuries. Others may represent entirely local innovations that never spread beyond the region. The unanswered questions surrounding Tidis resemble mysteries found throughout the ancient world. Machu Picchu demonstrates astonishing adaptation to mountainous terrain. Petra reveals extraordinary mastery of water management and rock-cut architecture. The Great Pyramid of Giza continues inspiring debate about surveying precision and construction logistics. Roman aqueducts illustrate hydraulic expertise on an immense scale. Tidis shares characteristics with all of these sites while presenting challenges unique to its own environment. Lung Kui Cave, hidden within the limestone mountains of Quan Ba district in Ha Giang province, northern Vietnam, presents a mystery unlike the lost cities, pyramids, or ancient temples that dominate archaeological documentaries. There are no inscriptions, no kings, and no forgotten civilizations here. Instead, Lung Kui poses a far stranger question. How did nature, using nothing more than water, minerals, gravity, and time, construct an underground world so complex that modern engineers still struggle to fully explain its formation? Officially surveyed and opened for scientific study in the early 21st century, The cave quickly attracted attention because of its extraordinary density of stalactites and stalagmites. Yet the deeper researchers look, the more they discover that Long Kui is not simply a cave. It is a natural laboratory preserving evidence of geological processes that have been operating for hundreds of thousands of years and perhaps much longer. The cave lies approximately 1,000 meters above sea level within the Dongvan Karst Plateau region, an area recognized for limestone formations dating back roughly 400 to 600 million years. The discovery itself was relatively straightforward compared to many archaeological sites. Local communities had long known of openings in the mountain, but systematic surveys revealed a vast underground network extending hundreds of meters through ancient limestone. What initially appeared to be a beautiful cave soon became something far more intriguing. Scientists realized that many of the formations inside represented geological growth processes that remain difficult to model with precision even using modern computer simulations. The first great mystery concerns the construction of the cave itself. Limestone caves form when slightly acidic water dissolves calcium carbonate rock over immense periods of time. The basic chemistry is understood. Rainwater absorbs carbon dioxide from the atmosphere and soil, creating weak carbonic acid capable of slowly eroding limestone. Yet understanding the chemistry is very different from explaining the final result. Long Kui contains chambers, corridors, columns, and intricate formations arranged in ways that often appear almost architectural. The volume of rock removed during the cave's formation likely reaches millions of cubic meters. To appreciate the scale, imagine excavating a vast underground cathedral without machinery, explosives, or tools. Nature accomplished precisely that. Researchers can describe the process, but accurately reconstructing every stage of cave evolution remains nearly impossible because tiny variations in water flow over geological timescales produce dramatically different outcomes. Even more puzzling is the formation of the cave's enormous stalactites and stalagmites. Some formations stretch several meters in height, while others have merged into massive columns connecting floor and ceiling. Modern measurements from caves around the world indicate that stalactites typically grow at rates ranging from about 0.1 to 3 millimeters per year, depending on mineral concentration, temperature, humidity, and water flow. At such rates, a column standing 5 meters tall may represent tens of thousands or even hundreds of thousands of years of continuous mineral deposition. Yet growth is not uniform. Two formations located only centimeters apart can develop entirely different shapes. One may become a slender needle, while another expands into a massive pillar. Scientists understand the general principles involved, but predicting the precise morphology of individual formations remains extraordinarily difficult. In effect, Long Kui contains geological structures whose development resembles a form of natural self-engineering, operating beyond direct human observation. Perhaps the most remarkable mystery involves what researchers call speleothems, the collective term for cave mineral formations. Many of Long Kui's formations display complex patterns that appear almost designed. Curtains of stone hang from ceilings like frozen waterfalls. Delicate calcite draperies twist into shapes resembling fabric. Flowstones spread across walls in layered sheets that evoke artificial construction materials. These forms emerge from the interaction of gravity, evaporation, mineral saturation, airflow, and microscopic surface conditions. The challenge is that even minor changes in one variable can completely alter the final result. Modern engineers designing advanced manufacturing systems often struggle with comparable complexity. Yet inside Long Kui, nature has been performing this form of mineral engineering automatically for millennia. Another mystery centers on the cave's environmental stability. Outside the cave, northern Vietnam experiences substantial seasonal variation. Temperatures may exceed 30 degrees Celsius during summer and fall below 10 degrees during winter. Humidity levels fluctuate dramatically throughout the year. Inside Lung Cui, however, conditions remain relatively stable. Temperature, moisture, and airflow exist within narrow ranges that have persisted over immense timescales. Modern facilities designed to preserve sensitive artifacts, rare biological samples, or high-performance computing equipment require sophisticated climate control systems to achieve similar stability. Lung Cui accomplishes this naturally. Scientists recognize that cave geometry, air circulation pathways, and thermal inertia all contribute to the phenomenon, but constructing precise models capable of predicting long-term cave microclimates remains a significant scientific challenge. The cave also functions as a geological archive of astonishing value. Every layer deposited within a stalagmite contains chemical information about the environment at the time of its formation. By analyzing oxygen isotopes, carbon isotopes, and trace elements trapped within calcite layers, researchers can reconstruct ancient rainfall patterns, monsoon strength, vegetation changes, and temperature fluctuations. Similar studies conducted in caves across Asia have revealed climate records extending back hundreds of thousands of years. In essence, the formations within Lung Cui operate like a natural hard drive, storing environmental data from periods long before human history was recorded. Yet decoding this archive is far from straightforward. Signals overlap, chemical processes modify original information. Growth interruptions create gaps in the record. Scientists can extract remarkable insights, but much of the information preserved within the cave remains difficult to interpret with confidence. One of the least understood aspects of Lung Cui involves the hidden water systems responsible for its creation. The cave visible today represents only a small fraction of a much larger karst network extending beneath the surrounding mountains. Water carved these passages over geological timescales, but the exact pathways followed by ancient underground rivers remain uncertain. Around the world, cave explorers continue discovering new chambers in systems once believed fully mapped. In some regions, surveys have expanded known cave lengths from a few kilometers to hundreds of kilometers. The world's longest cave system, Mammoth Cave in Kentucky, exceeds 680 kilometers of mapped passageways, and exploration continues. This raises a fascinating question. How much of the underground landscape beneath Hajiang remains unknown? Despite advances in ground-penetrating radar, laser scanning, and geophysical imaging, mapping complex karst systems remains one of the most difficult challenges in geology. The age of the surrounding rock introduces another layer of mystery. The limestone forming much of the Dongvan Karst Plateau originated in ancient seas hundreds of millions of years ago, long before dinosaurs appeared. Marine organisms accumulated on prehistoric seabeds, eventually forming thick carbonate deposits. Tectonic forces later uplifted these rocks into mountains. Water then began carving caves through them. The result is a geological timeline spanning an almost incomprehensible duration. To place this in perspective, the entire history of human civilization occupies only a tiny fraction of 1% of the time represented by these rocks. Lung Cui is therefore not merely a cave, it is the visible outcome of processes operating across intervals so vast that they challenge human imagination. What do you think? Does Lung Cui Cave simply showcase the power of geology over immense timescales? Or does it reveal levels of natural engineering that modern science still cannot fully explain? Let us know your thoughts in the comments below. Roman engineers built many extraordinary cities across the ancient world, but almost all of them followed one simple rule: build where the land is easy to control. Jamila broke that rule completely, perched nearly 900 meters above sea level in the rugged mountains of northeastern Algeria. This ancient city was constructed on uneven slopes, rocky ridges, and narrow valleys that should have made large-scale urban planning nearly impossible. Yet nearly 2,000 years later, its streets, forums, temples, drainage systems, and monumental structures remain among the best-preserved Roman ruins anywhere on Earth. The mystery is not that Jamila survived. The mystery is how it was built in the first place. Jamila, known in antiquity as Quiquel, lies in present-day Algeria, approximately 50 kilometers northeast of Sétif. The site was formally identified and explored during the 19th century after French expeditions documented extensive Roman ruins emerging from the mountainous landscape. Subsequent excavations throughout the late 19th and 20th centuries revealed a remarkably intact city founded around 96 CE during the reign of Emperor Nerva. Archaeologists expected to find a typical Roman colonial settlement. Instead, they discovered one of the most unusual examples of ancient engineering adaptation ever documented. The first and perhaps greatest mystery concerns urban planning. Roman cities were famous for their grid layouts. From Timgad in Algeria to numerous settlements throughout Europe and the Middle East, Roman surveyors preferred flat terrain where streets could intersect at near-perfect right angles. Jamila, however, occupies terrain that seems fundamentally incompatible with such planning. The city stretches across irregular elevations separated by natural obstacles and steep gradients. Yet excavations show that Roman engineers successfully imposed a structured urban design onto this chaotic landscape. Modern topographic analysis reveals remarkable alignment between major streets and public buildings, despite significant differences in elevation. This raises a fascinating question. How did Roman surveyors achieve such precision? They possessed no satellites, laser levels, electronic instruments, or aerial maps. Their primary tools included devices such as the groma for establishing straight lines and the chorobates for measuring gradients. These instruments were effective, but applying them across mountainous terrain required an extraordinary understanding of geometry and spatial planning. Modern civil engineers often rely on sophisticated surveying equipment to solve similar challenges. The accuracy achieved at Jamila suggests that Roman surveyors possessed practical expertise that may have exceeded what surviving texts alone can explain. Equally puzzling is the city's hydraulic engineering. Water management represented one of Rome's greatest technological achievements, but Jamila presented unusual difficulties. Mountain environments experience rapid runoff during seasonal storms. Without effective drainage, streets erode, foundations weaken, and buildings collapse. Yet archaeological investigations have revealed a sophisticated network of channels, underground drains, and carefully engineered slopes designed to control water flow throughout the city. The effectiveness of this system becomes even more impressive when viewed through modern engineering principles. For gravity-driven drainage to function properly, gradients must remain within carefully controlled ranges. Too steep and erosion accelerates, too shallow and water stagnates. Measurements taken at several surviving drainage structures indicate remarkably consistent gradients despite the difficult terrain. Similar hydraulic precision can be observed in famous Roman aqueducts such as the Pont du Gard in France, where average slopes often measured only a few centimeters per 100 meters. Jamila demonstrates that comparable engineering precision extended beyond aqueducts into the broader design of entire urban landscapes. Another mystery involves the massive retaining structures that allowed the city to expand across uneven ground. Throughout Jamila, Roman builders constructed terraces supported by stone walls capable of resisting enormous lateral pressures from soil and rock. Many remained standing despite nearly 2 millennia of earthquakes, weathering, and environmental stress. Modern geotechnical engineering relies on mathematical calculations to estimate soil pressure, foundation loads, and structural stability. Roman engineers lacked modern equations, yet many of their retaining walls have outlasted countless newer structures. The question becomes even more intriguing when considering construction methods. Some retaining structures consist of carefully fitted stone blocks with minimal mortar. Similar techniques can be seen at sites such as Machu Picchu and Sacsayhuaman in Peru, where precisely fitted masonry contributes to earthquake resistance. Although separated by continents and centuries, these civilizations independently developed solutions that continue to impress modern engineers. At Jamila, researchers still debate how Roman builders optimized wall placement and dimensions to maximize long-term stability without modern geological analysis. Transportation presents another unsolved challenge. The monumental architecture of Gemila required enormous quantities of stone. Columns, capitals, paving blocks, statues, and structural elements weighing several tons had to be transported through mountainous terrain. Ancient sources describe Roman use of rollers, sledges, cranes, and animal power, but the logistics remain staggering. Estimates from comparable Roman construction projects suggest that moving a single large column could require dozens of workers and complex mechanical systems. The mystery is not simply how these materials were moved, but how such transportation was organized efficiently on a large scale. Jamila's public buildings include temples, baths, basilicas, markets, and triumphal monuments, all requiring coordinated supply chains. Similar questions surround other famous Roman sites such as Baalbek in Lebanon, where individual stone blocks exceed 800 tons. While Jamila's stones were smaller, the mountainous environment introduced additional challenges that remain difficult to reconstruct with certainty. One of the most intriguing aspects of the city is the expansion known as the New Forum. By the 3rd century CE, Jamila's population had grown beyond the capacity of its original urban core. Instead of relocating development to more favorable terrain, Roman authorities undertook an ambitious expansion involving extensive earthworks and structural modifications. Archaeological evidence indicates that significant portions of the landscape were reshaped to accommodate new public spaces. This decision raises important questions. Why invest enormous resources into modifying difficult terrain when alternative locations existed nearby? Some historians suggest political motivations. Monumental architecture often served as a display of imperial power. Constructing a grand forum in a technically challenging location may have been intended to demonstrate Rome's ability to dominate nature itself. If true, Jamila represents not only an engineering achievement, but also a statement of political ideology expressed through urban design. The city's resilience against seismic activity provides another enduring puzzle. Northern Algeria lies within a tectonically active region influenced by interactions between the African and Eurasian plates. Numerous earthquakes have affected the region throughout history. Despite this, substantial portions of Jamila remain standing. While many structures suffered damage, the overall survival rate of major architectural elements is remarkable. Researchers continue to investigate whether certain construction techniques inadvertently improved earthquake resistance. Large stone blocks, flexible masonry joints, and distributed structural loads may have contributed to the city's longevity. Similar debates surround the survival of Roman structures elsewhere, including the Pantheon in Rome, whose massive dome remains the largest unreinforced concrete dome ever built nearly 2,000 years after construction. Gemilla may contain additional clues about ancient approaches to structural resilience that remain poorly understood. Among the most visually stunning discoveries are the city's mosaics. Excavations uncovered intricate floor mosaics displaying extraordinary craftsmanship and artistic sophistication. Yet these artworks also raise technological questions. The pigments used in Roman mosaics often retained vivid coloration for centuries despite exposure to environmental stress. Researchers studying ancient pigments have identified complex mineral compositions involving iron oxides, carbon compounds, and other naturally occurring materials. In some cases, ancient coloration techniques demonstrate durability that rivals or exceeds certain modern materials. Perhaps the deepest mystery of Gemilla is not any individual structure but the knowledge system behind them all. Every street alignment, drainage channel, retaining wall, public monument, and architectural feature reflects accumulated expertise developed over generations. Roman engineers clearly understood principles of surveying, hydrology, materials science, logistics, and structural design at a remarkably sophisticated level. Yet much of their practical knowledge vanished with the decline of the Western Roman Empire. Volubilis, northern Morocco. Nearly 2,000 years ago, this Roman city operated one of the largest olive oil industries in North Africa. Today, dozens of ruined presses remain scattered across the site. At first glance, they appear simple, yet the engineering behind them continues to raise questions that archaeologists and engineers still cannot fully answer. Excavations conducted throughout the 20th century uncovered more than 50 olive oil production installations across Volubilis. Archaeologists found crushing stones, pressing rooms, settling tanks, counterweights, drainage channels, and industrial workshops. Together, these discoveries revealed an ancient manufacturing system operating on a scale far larger than previously imagined. Volubilis occupied a surprising location. The city stood more than 2,000 kilometers from Rome and far from many of the empire's major commercial centers. Yet archaeological evidence suggests olive oil production formed one of the foundations of its economy. Researchers have identified dozens of presses operating simultaneously, and some estimates suggest thousands of liters of oil could have been produced during a single harvest season. This immediately creates a logistical puzzle. Olive oil was one of the most valuable commodities in the Roman world. It served as food, fuel for lamps, medicine, cosmetics, and religious offerings. Producing it on such a scale required enormous agricultural infrastructure. Thousands of olive trees had to be cultivated, harvests had to be organized within narrow seasonal windows, workers had to transport fruit quickly before spoilage began, and finished oil then had to be stored and distributed across regional trade networks. Even modern agricultural operations depend heavily on transportation systems and centralized coordination. Yet Volubilis achieved industrial-scale production with animal power, human labor, and mechanical technology that appears deceptively simple. How this remote city sustained such output remains one of its first great mysteries. Among all the technological puzzles of Volubilis, none may be more fascinating than the presses themselves. At first glance, they appear primitive. Most consisted of long wooden beams attached to stone counterweights. Workers gradually increased pressure by tightening ropes, adding weights, or manipulating mechanical components connected to the beam. The system seems straightforward until engineers examine the forces involved. Olive pulp cannot simply be squeezed lightly. Efficient extraction requires tremendous pressure distributed evenly across stacked baskets filled with crushed olives. Too little force leaves valuable oil trapped inside, while too much force damages equipment or contaminates the product. Modern hydraulic presses achieve this using steel cylinders, pressure gauges, and precisely engineered components. The Romans possessed none of these technologies, yet archaeological reconstruction suggests some volubilis presses may have generated several tons of effective pressure through mechanical advantage alone. The secret lies in leverage. A beam several meters long can multiply force dramatically when combined with carefully positioned fulcrums and counterweights. What appears to be a simple wooden structure can function as a powerful force-amplifying machine. This raises a remarkable question. How did Roman engineers determine the optimal dimensions? No blueprints survive. No technical manuals from volubilis explain the calculations. No engineering records describe how builders selected beam lengths, counterweight masses, or support structures. Yet the surviving installations display striking consistency. Many presses follow similar proportions despite being constructed in different locations and at different times. Some researchers believe Roman craftsmen possess practical engineering knowledge passed through generations of specialists. Others argue that extensive experimentation gradually refined the designs. Either explanation implies a level of mechanical understanding far beyond what many people imagine when thinking about ancient agriculture. Experimental archaeologists attempting to recreate Roman presses have discovered that small design changes can dramatically affect efficiency. A slight alteration in beam length changes force multiplication, a minor shift in pivot location alters pressure distribution, and a different counterweight mass affects extraction rates. In other words, these machines worked because somebody understood mechanical principles with remarkable precision. The machines themselves survived, but the knowledge that created them largely disappeared. The presses depended on another technological achievement often overlooked: stone. Large crushing wheels, grinding basins, support blocks, and counterweights had to be carefully shaped and balanced. Some crushing stones discovered at volubilis display impressive symmetry. Their geometry allowed relatively smooth rotation despite being carved centuries before precision machine tools existed. Creating such components required skilled quarrying, stone cutting, transportation, and finishing techniques. A poorly balanced stone would generate vibration, reduce efficiency, and accelerate wear. The surviving examples suggest craftsmen understood practical tolerances surprisingly well. The challenge becomes even more impressive when considering scale. Many stones weighed hundreds of kilograms, and some structural components likely exceeded a ton. Moving them required coordinated labor and sophisticated logistical planning. Exactly how these operations were organized remains uncertain. Another puzzle emerges when comparing different production facilities. Many workshops share remarkably similar layouts. Press rooms frequently contain comparable dimensions. Settling tanks follow familiar patterns, and drainage systems repeat the same engineering solutions. Such consistency suggests standardization. Modern factories rely on standardized designs because they improve efficiency and simplify construction. Volubilis appears to have followed a similar principle nearly 2 millennia ago. Yet no architectural plans have been found. No manuals explain the measurements, and no records identify the engineers responsible. The city presents evidence of a coordinated industrial system without preserving the documentation that would explain how it operated. Producing olive oil involves far more than crushing olives. Separating oil from water and organic residue is a complex process. The settling tanks discovered at volubilis reveal an understanding of fluid behavior that appears surprisingly sophisticated. After pressing, liquid mixtures entered a sequence of basins where gravity gradually separated different substances according to density. Oil floated upward, while water and sediment settled below. The concept seems obvious today because modern science explains it through physics and chemistry. Ancient producers lacked such theoretical frameworks. Nevertheless, they developed systems capable of producing high-quality oil that supplied markets throughout the Roman world. This suggests centuries of accumulated practical experimentation. Exactly how that knowledge evolved remains unknown. Energy was one of Volubilis's greatest challenges. Every step from harvesting olives and operating presses to transporting oil required human or animal labor. Unlike modern factories powered by electricity, Volubilis depended almost entirely on people and animals. Supporting dozens of presses likely required the effort of entire communities during harvest seasons. The city resembled an ancient industrial complex, yet how such a large workforce was organized remains unknown. Do you think the engineers of Volubilis developed these powerful olive presses through centuries of trial and error? Or did they possess mechanical knowledge that has largely been lost to history? Share your thoughts in the comments below. Yerevan, Armenia. On a volcanic hill overlooking the Ararat Plain stands a fortress nearly 2,800 years old. Most ancient paint should have vanished long ago. Yet inside Erebuni Fortress, colours still survive, and nobody fully understands why. In 1950, Soviet archaeologists excavating Arenberg Hill uncovered the remains of Erebuni Fortress, a royal stronghold founded in 782 BC by King Argishti I of the Kingdom of Urartu. The discovery revealed massive fortifications, administrative buildings, giant storage rooms, and one of the most unexpected finds in ancient archaeology. Large sections of painted walls whose colours remained visible after almost 28 centuries. Erebuni was built during an age when most settlements relied on mud brick structures vulnerable to weather, earthquakes, and war. The fortress occupied roughly 8 hectares and sat atop a strategically chosen hill approximately 65 meters above the surrounding plain. Its foundations were constructed from basalt blocks, while upper sections used mud brick walls that once reached heights of more than 10 meters. What puzzles engineers today is the fortress's longevity. Armenia lies within one of the most seismically active regions of the Caucasus, and historical records as well as geological studies indicate repeated destructive earthquakes across the region throughout the past 2 millennia. Yet significant portions of Erebuni survived. Some researchers suggest that the combination of heavy stone foundations and lighter mud brick superstructures may have unintentionally created a primitive form of seismic resistance. Modern earthquake engineering often relies on the same principle, as lower structural mass reduces destructive forces during seismic events. Whether the Eurasians understood this scientifically remains unknown. What is clear is that their construction methods worked far better than many contemporary fortifications. Among all the discoveries at Erebuni, nothing has generated more fascination than its wall paintings. Most ancient pigments degrade rapidly. Ultraviolet radiation breaks molecular bonds, moisture causes chemical reactions, and temperature fluctuations create microscopic fractures. Over centuries, colours fade. At Erebuni, many did not. Archaeologists discovered extensive murals featuring vivid reds, blues, blacks, whites, and yellows. These paintings depicted gods, sacred trees, geometric motifs, processions, and royal symbolism. Some pigments remained recognizable after nearly 2,800 years. To understand how extraordinary this is, consider the numbers. The paintings were already ancient when Rome was founded. They were over 700 years old when Alexander the Great entered Asia. They had existed for nearly 2,000 years when medieval castles appeared across Europe. Yet traces of their original colours still remained. This raises a technological mystery. How were these pigments produced? Scientific analysis indicates that many colours came from carefully selected mineral sources. Red pigments were likely derived from iron oxides. Black pigments may have originated from carbon-based materials. White pigments often contained calcium-rich compounds. Blue pigments remain especially intriguing. Blue is one of the most difficult colours to produce in the ancient world. The famous Egyptian blue, created more than 4,000 years ago, required heating silica, copper compounds, lime and alkali materials to temperatures approaching 900 to 1000 degrees Celsius. Its production demanded precise control of chemistry and temperature. Some researchers believe Urartian craftsmen possessed similarly advanced knowledge of mineral processing. The challenge is that no manufacturing manuals survive. No written recipes explain how pigments were prepared. No workshop instructions have been found. Only the results remain. Even more puzzling is the durability of the pigments. Laboratory studies show that many ancient paints deteriorate rapidly when exposed to moisture and sunlight. Yet Erebuni's colours survived despite centuries of environmental exposure. Why? Several competing explanations exist. Some scientists argue that the mineral composition itself was unusually stable. Others believe the plaster beneath the paint played a crucial role. The plaster may have chemically bonded with pigments, creating a protective matrix that slowed degradation. A third theory suggests that environmental conditions inside collapsed structures shielded portions of the artwork from direct weathering for centuries. None of these explanations fully solves the mystery. Experimental archaeologists attempting to recreate ancient pigments often discover that seemingly simple mixtures behave differently depending on microscopic impurities, firing temperatures, and preparation methods. A variation of only a few percentage points in mineral composition can dramatically affect durability. Without complete knowledge of Urartian production techniques, modern researchers cannot perfectly reproduce the original results. The colours of Erebuni may therefore represent a technological process that remains only partially understood. Like Roman concrete and Egyptian blue, they belong to a category of ancient materials whose secrets have not been completely recovered. The fortress itself presents another engineering mystery. Thousands of tons of stone, timber, clay, and construction materials had to reach the summit of Arinbird Hill. The builders possessed no cranes, diesel engines, hydraulic lifts, or modern machinery, yet construction proceeded on a monumental scale. Comparisons with other ancient projects reveal the challenge. The Great Pyramid of Giza required the movement of approximately 2.3 million stone blocks. Stonehenge involved transporting megaliths weighing up to 25 tons. While Erebuni was smaller, it still required extensive logistical coordination. The unanswered question is how Urartian engineers organized labor, transportation, and material supply chains with such efficiency. No records describing construction procedures have survived. A fortress cannot function without water, and this creates another mystery. Erebuni occupied elevated terrain where natural water access was limited. Archaeological evidence suggests sophisticated storage and distribution systems once existed. Researchers have identified cisterns, channels, and water management features connected to the fortress. However, significant portions of the system have disappeared. The surviving evidence suggests a level of hydraulic planning far beyond what many people associate with Iron Age societies. How much of that system has been lost remains unknown. Perhaps the greatest mystery is not the fortress itself, but the knowledge that created it. The Kingdom of Urartu built impressive fortresses across the Armenian highlands, mastering construction, engineering, and art. When the kingdom collapsed in the 6th century BC, its power faded, its traditions fragmented, and much of its knowledge disappeared. Only the monuments remained. This pattern appears throughout history. The builders of the Great Pyramid, the creators of the Antikythera mechanism, and the engineers behind Roman concrete all left remarkable achievements but few explanations. Erebuni belongs to the same category. Its walls, pigments, and engineering survive, yet many of the methods behind them remain unknown. Nearly 2,800 years later, researchers can analyze the site with advanced technology, but key questions remain. How were the pigments made? Why did they last so long? What knowledge did Urartian craftsmen possess? The colors of Erebuni continue to challenge modern assumptions. Sometimes the greatest archaeological mystery is not what was lost, but what somehow survived. Do you think the enduring colours of Erebuni were simply the result of exceptional natural materials, or did the Eurasians possess advanced chemical knowledge that history has largely forgotten? Share your thoughts in the comments below. Leptis Magna stands on the Mediterranean coast of present-day Libya, approximately 130 kilometers east of Tripoli. Today it is considered one of the best preserved Roman cities in the world. Although the site was known locally for centuries, systematic archaeological excavations began during the late 19th and early 20th centuries, revealing an enormous urban complex buried beneath sand dunes. What researchers uncovered was not merely another Roman city. It was an engineering masterpiece whose most impressive technologies remain only partially understood. At first glance, Leptis Magna appears to be a monument to Roman wealth. Massive basilicas, colonnaded streets, marketplaces, bath complexes, warehouses, harbours, and public monuments cover hundreds of hectares. Yet the deeper archaeologists investigate, the more difficult questions emerge. How did an ancient city flourish on such a scale in an environment where water was scarce, coastal conditions were hostile, and construction materials often had to travel extraordinary distances? The greatest mystery begins with water. Modern satellite imagery and archaeological surveys reveal that Leptis Magna depended on an extensive hydraulic network. Annual rainfall in the region averages only a few hundred millimeters, yet the city supported a population estimated by some historians to have exceeded 80,000 people during its peak under Emperor Septimius Severus in the late 2nd and early 3rd centuries AD. Public baths alone consumed vast quantities of water every day. Roman engineers constructed reservoirs, cisterns, channels, and aqueduct systems that collected seasonal runoff from distant valleys. The challenge is that many sections of this infrastructure remain buried or destroyed. Researchers know the system worked, but they still cannot fully reconstruct how water was collected, stored, distributed, and maintained across such a large urban area. The engineering resembles the hydraulic achievements of Petra in Jordan, where water management transformed an arid landscape into a thriving city. Yet Leptis Magna operated on an even larger urban scale. The harbour presents another unresolved puzzle. Leptis Magna became one of the most important commercial ports in North Africa. Thousands of tons of olive oil, grain, livestock products, and luxury goods moved through the city. Archaeological remains reveal extensive harbour installations, breakwaters, and docking facilities. However, modern geomorphological studies show that the coastline was vulnerable to sediment accumulation. Rivers transported silt toward the harbour basin, while coastal currents deposited additional material. Many ancient ports facing similar conditions gradually became unusable, yet Leptis Magna remained an active commercial centre for centuries. Some researchers believe Roman engineers regularly dredged the harbour. Others suggest sophisticated breakwater designs altered water circulation patterns to reduce sediment buildup. No surviving Roman document explains exactly how the problem was solved. The mystery resembles ongoing debates surrounding the harbours of Alexandria and Ostia, where engineers appear to have possessed a practical understanding of coastal dynamics that exceeded what historians once assumed. Another technological enigma involves construction materials. Numerous structures at Leptis Magna survived nearly 2,000 years despite exposure to salt-laden air, humidity, seasonal temperature changes, and occasional seismic activity. Modern concrete frequently deteriorates within decades under comparable conditions. Roman concrete has become one of the most studied ancient materials because scientific analyses reveal unusual mineral formations that continue strengthening structures over time. At Leptis Magna, researchers have identified construction techniques that combined local stone, imported materials, lime-based mortars, and carefully engineered foundations. Yet many details remain uncertain. Did North African builders use specialized material recipes adapted to coastal conditions? Were regional construction methods different from those employed elsewhere in the empire? Similar questions surround Roman maritime concrete, some examples of which have survived nearly 2 millennia in seawater. The durability of Leptis Magna suggests that significant aspects of Roman material science remain incompletely understood. The transportation of construction materials presents another astonishing challenge. The city contains enormous columns of granite and marble. Some granite originated in Egypt, over 1,500 kilometers away. Individual columns weighed tens of tons. Moving such objects required quarrying, shaping, transporting, loading onto ships, unloading, hauling inland, and erecting them with remarkable precision. Modern construction relies on cranes, hydraulic systems, steel cables, computerized logistics, and heavy transport vehicles. Roman engineers possessed none of these technologies. Archaeologists have reconstructed possible methods involving wooden cranes, capstans, pulleys, rollers, and specialized transport ships. Yet calculations demonstrate the extraordinary organizational complexity required. Like the builders of the Great Pyramid of Giza, Roman engineers achieved results that remain difficult to replicate even when the general principles are understood. Urban planning provides another layer of mystery. Aerial surveys reveal a remarkably organized city layout. Major roads intersected public spaces with impressive precision. Commercial districts, administrative centers, religious complexes, and residential neighborhoods were integrated into a coherent urban design. Surveyors achieved accurate alignments across large distances without GPS, satellites, lasers, or modern mapping systems. Roman surveyors used tools such as the groma and curabates, but historians continue debating how these relatively simple instruments produce such consistent results. Similar questions arise at Priene in Turkey and the Roman colonial cities of North Africa, yet Leptis Magna represents one of the largest and most ambitious examples of ancient urban planning. Perhaps the most underestimated mystery concerns logistics. During the reign of Septimius Severus, who was born in Leptis Magna in AD 145, the city underwent an enormous construction program. The Severan Forum, Severan Basilica, monumental arches, expanded streets, and public infrastructure transformed the city. Archaeological evidence suggests that construction occurred over a relatively short period. Managing such projects required coordinating thousands of workers, securing raw materials, transporting supplies, feeding labor forces, maintaining tools, and ensuring architectural consistency. Modern mega-projects depend on computers, telecommunications, digital planning software, and advanced management systems. Roman administrators relied entirely on human organization. The fact that these projects were completed successfully remains one of the most impressive logistical achievements of the ancient world. The city's decline is itself a mystery. Historical sources describe political instability, economic disruptions, invasions, and environmental changes. Earthquakes may have damaged critical infrastructure. Trade routes shifted, administrative priorities changed. Yet no single event explains why one of Rome's most prosperous cities gradually faded. Like many ancient civilizations, Leptis Magna appears to have succumbed to a combination of interconnected pressures. Over centuries, sand reclaimed streets that once carried merchants from across the Mediterranean. Today, laser scanning, satellite imaging, geophysical surveys, materials science, and computer modeling allow researchers to study Leptis Magna with technologies unimaginable to its builders. Archaeologists can analyze mortar chemistry at the microscopic level, map buried structures without excavation, and reconstruct ancient environments using digital simulations. Yet despite these tools, some of the most important questions remain unanswered. How exactly did the water system function at full capacity? How was the harbour maintained against natural sedimentation? What material technologies contributed to the city's remarkable durability? How were enormous construction projects organised so efficiently? And how much technical knowledge disappeared when the Roman world entered decline?